Very good morning, Dr. Senthil.
Hi, good morning, Lena. Good morning, everyone.
Good morning, sir.
Good morning, sir. Good morning, Lena.
Morning, sir.
I'll just take 2 minutes, sir, as the students are also joining.
Yeah, sure, Lena.
Yeah, so we have a 10-mark quiz remaining class. So that I'll be releasing today itself, and I'll give the time till 6th March. Because 6th March is our graded assessment. And we have 2 assignments remaining for the session 5 and session 6, right? So those assignments also I'll be releasing
Lena
today.
ma'am, seems like you're talking, but it's in mute, I guess.
No,
I think
No,
we
I am
can
able
we
to
can hear
hear.
you. Yeah, we will do.
Yeah.
Okay, yeah. I'll put it in the group also, Maheshwari. So these are the 2 deliverables remaining from our side for ML2. So mandatory and optional also I'll release today itself, so that you'll get sufficient time to start with it for session 5 and session 6 both, right? And presentations also the dates are given, right? I hope all of you are aware of it. Okay. So any other doubts you can ask, or we can start with the session. Okay.
Are
Sure.
we going to have a continuation of random forest or because
Come back, Satya. I'm not able to hear. Come back.
no, is this a continuation of session 5 on random forest or are we going to take a new algorithm? Because if a brief overview will be helpful. It's been 6 weeks now.
Yeah. Sir will be there. Sir will be taking. Sir will be bringing you on to the that is there. Yeah, you asked with respect to quiz or with the session?
No. Today's session.
Yeah, definitely. Sure. So I'll stop the sharing and yeah, that's it, sir, from my end.
Yeah, thank you, Lena. So I think including you and me, 15 participants are here. Shall we start or I will wait for 1 more minute or 2 more minutes? Fine. Fine, we can start then. Once again, very good morning to all. So it was long time before actually we have discussed different classification concepts, and after that a kind of long gap. But anyway, so in today's session, I will be quickly refreshing those algorithms also that we have discussed in our previous session. But the main agenda for today's session is we are going to discuss few more ensembling algorithms. So if you remember, we have already discussed 2 ensembling algorithms, one in detail, that is random forest. The another one is, while we're discussing the random forest itself, we have discussed the concept behind bagging, because bagging is actually part of your random forest. Along with a typical bagging, one more extra thing, that is column sampling. Also, we have incorporated in that random forest algorithm, right? So that is the 2 ensembling techniques that we have discussed in our previous session, bagging and random forest. In today's session, we are going to discuss few more ensembling techniques like boosting, voting, and stacking. So that is the main agenda for today's session. The 3 ensembling techniques: boosting, voting, and stacking. We are going to first discuss its mathematics, discuss its concepts, and we are going to implement that in Jupyter Notebook, right? So what I can do is quickly, before starting the boosting, I will quickly refresh the other 2 ensembling technique, which is nothing but random forest and bagging. Then from there we can just smoothly move into boosting, as we had some long gap in between. So let me start with the quick recollection of what we discussed under bagging and random forest ensembling technique. Let me take you to a board. Let me share my screen. Fine. So in this ML2 course, we started with the discussion of logistic regression, which typically a kind of linear model, because a clear explanation about the output for every input is possible through logit ratio or through odds ratio in case of logistic regression. So that is the reason why we have called that as a linear model. Apart from logistic regression, whatever the other model that we have discussed in our residency, it's actually a kind of non-linear models. Of course, we discussed one algorithm which is actually Bayes, that is naive Bayes, which is actually a pure statistical or pure probabilistic based model. Apart from that, all other models like a decision tree, KNN, random forest, bagging, all those things that we have discussed are actually non-linear machine learning model. Why we are calling this as nonlinear machine learning model, we have discussed in our previous session, because it is not actually using the same strategy to make decision about all the observation. What I mean by same strategy in the sense, in logistic regression, once you come up with that one equation for P equal to exponential of y reg divided by 1 plus exponential of y reg, once we computed that parameters related to that particular expression or particular P value, for any given input, we are going to compute those B0, B1, all those coefficients. Once we compute those coefficients, we are going to apply that in that P formula, and we are going to get what is the probability that that particular observation belongs to class 0 or belongs to class 1. So that is very straightforward, and this equation, that coefficients that we are computing is actually remains same irrespective of whatever the input that you apply into your model, right? In decision tree also, but in decision tree, if you see, we have a multiple path from the root node to your leaf node, right? So you may, for one decision tree construction, we may have multiple leaf node. The characteristics of the leaf node is it should be as pure as possible, right? Ideally speaking, all the leaf nodes, the last node in your decision tree, are completely homogeneous. Homogeneous means it belongs to a complete single one class. But say my objective is to predict whether the person is having cancer or not. In my decision tree, there are so many leaf nodes which actually corresponding for cancer, and also there are so many leaf nodes which actually corresponding to non-cancer, which means from the root node, my programming flow will go in a different path to reach the same class, decision. It is not like whenever I'm going to take the decision as the patient is having cancer, I'm not going to travel in the same path of the decision tree. Whereas in logistic regression, the same equation only has been used for each and every input. Whereas in decision tree, say, for example, let me write here, let me quickly say for a decision tree, it may go in this path and it will reach on a root node where all the samples are belongs to cancer, right? Or majority of sample belongs to cancer. So we are making like, if whenever my data is flows, my test data is flows in this path and reaching that leaf node where the cancer cases are dominant, for that test input, we are making the classification decision as that patient is having cancer. But there could be some other path. In this decision tree, which is, say, after, say, here I have one another split, then one another split, then one another split, then one another split, like that. We have multiple splits, no? So there may be one another path also like this. Which will actually take you to cancer leaf, which will actually taken to cancer leaves. So it is quite possible that you can travel through multiple paths to reach or to take the same classification decision, right? So that is the reason why decision tree is actually known as nonlinear model. It is not actually doing the process in the same way in predicting the cancerous class or predicting one class. So it will actually, based upon the data that we have, based upon the time data that we had, it is actually construct the multiple path to make the decision about cancer. Similarly, multiple paths to make the decision about the non-cancer. So that is the reason why it is actually known as non-linear model. We can't straight away formulate this one straight equation for all the, or one equation or one structure for all the input. For each and every input, the flow may be different. So this is about a decision tree that we have discussed, and we have discussed in decision tree, how can we choose the root node, how can we choose the next level nodes. We can use the concept of Gini impurity, we can use the concept of entropy gain. So Gini impurity must be as minimum as possible, so that we can consider that as an root node, right? Among different feature, which feature is having the Gini impurity value less, that we are going to consider as the first root node, and based upon that we are going to split further until all my leaf nodes are become pure, right? So this is how the decision tree works. So basically decision tree is an non-linear model. So all other different ensembling techniques mostly is using the decision tree, like bagging. In bagging, you can use the base model as a decision tree, and also bagging will support some other base models also. You can construct the bagging using logistic regression. You can construct the bagging using KNN, right? So also you can construct the bagging using decision tree. But apart from bagging, random forest and boosting, these are all the kind of algorithms generally using the decision tree lot. And of course, for a random forest, the base learner must be your decision tree. So as decision tree is a nonlinear model, so as a decision tree, if you use as a kind of base learner, then obviously all other models also become a nonlinear model, right? So, and also in random forest and in bagging, we are not going to construct one decision tree, we are going to construct the multiple decision trees. As we are constructing the multiple decision trees, we are ensembling all the results, or we are consolidating all the results which is produced by each and every decision tree or each and every base learner, and we are taking the final decision. That is the reason why bagging random forest algorithms are known as ensembling algorithm. Of course, there are a few other ensembling algorithms also that we are going to discuss in today's session. But anyway, with respect to what we have discussed, bagging and random forest, we used to call it as an ensembling algorithm. Why it is ensembling algorithm? Because bagging or random forest is having so many base learner. Mostly the base learner is decision tree. Always the base learner is decision tree in random forest, but in bagging you can use some other machine learning model also as a base learner, but preferably it is a decision tree mostly, even in bagging. So once you construct the multiple decision tree, whether in bagging or random forest, each and every decision tree are independent of each other. So each and every decision tree will take its own decision. Then at last we have to consolidate all these decisions, and we are going to make one decision about that one single input. So that is the reason why, as we are consolidating all those results, we are calling this as an ensembling techniques. So now quickly I will summarize the steps of random forest. While we are summarizing that itself, we will just quickly summarize the bagging also. Then we will move into boosting, because while we are studying boosting, that understanding of how boosting is differ from bagging, or how boosting is differ from random forest, is very, very important. For that reason only, quickly I will revise the steps of random forest and bagging now quickly. Then later on, after we finish those ensembling techniques, even if you have any queries with respect to other models like logistic regression, Kane and Naibase, you can ask. We can quickly refresh those things also. Right. So now, so let me straight away start with random forest. Quick revision. So in random forest, of course, it is an ensembling technique. So we have to construct multiple decision tree. So how we can construct the multiple decision tree? I'm just going to have only one data set with me, right? So with one single data set, how can we construct the multiple decision tree? Can anyone recollect? Say my data set size is, say, 1000 cross 10. This is my data set size. This is my data set size. So now I want to construct the random forest algorithm on this data, right? So 1000 observation and 10 input column. Of course, that is one input column. If you include one output column also, then obviously it is 11 column of data. But anyway, say whatever I have written, it's nothing but input data size. So with respect to this 1000 cross 10 data set size, how it is possible to construct the random forest? What is the first thing that we need to do?
Random samples and random features.
Exactly. So in order to construct the in the process of building the random forest model, we have to construct multiple decision tree. So how it is possible to construct the multiple decision tree? If there is only one decision tree for one data set, you can easily compute how for this 10 features you will be finding the Gini impurity, right? So it is having 10 input feature. For all the 10 input feature, you are going to find the Gini impurity, and you are going to see which feature is having the least Gini impurity. Then with respect to that feature, you are going to split your data. Then after doing the first level of splitting, some out of this 1000 data, say 700 data is coming on the right side node, and 300 data are going on the left side node. In the sense, again, with respect to that 7000 data, you are going to find the Gini impurity for each and every column, and whichever the column which is having the less Gini impurity, based upon that, you are going to split it further. So similarly, that process you are going to do throughout until all the nodes become kind of more homogeneous. So that is how we will be constructing the decision tree. Now in random forest, of course, we are going to construct the decision tree, but multiple decision tree we have to construct. For that process, what we need to do is we have to first take the bag of data, right? So we have to do the process called bootstrapping. We have to do the concept. We have to apply the concept called bootstrapping. This is nothing but bag of data, right? So we are not actually using all those 1000 observations. We are going to use say some 60% of the data that you can even consider as an hyperparameter, and you can play with back samples hyperparameter while you are implementing your random forest. Say and also we have discussed one mathematical equation, n 1 divided by n is the probability that this sample not belongs to that particular bag, right? Using that, people say that generally if you go by some strategy, you will be getting 66% of the data in each and every bag, whatever. But anyway, there's an hyperparameter. You can build your model with 80% of data, or 60% of data, or 70% of data. So basically, this is actually row sampling. Basically, this is row sampling with replacement. Row sampling with replacement. So which means out of those 1000 data, I'm just going to selectively take some rows, right? So selectively means randomly only. So I'm going to select some rows randomly. So randomly, say 60% of rows has been selected by your algorithm. So this selection process we are going to do with a concept called with replacement, which means in the first bag, if I get this 60% of the data, in the second bag, some of the data which is already there in the first bag can repeat, right? So which means if I allow replacement, if I allow the repeatness, then obviously I can construct n number of bags. I can derive n number of bags from this 1000 data. So that is actually a row sampling, which means I can take this subset from this 1000 whole data. I can form so many subset of data. So many subset of data by randomly choosing some samples, randomly choosing some percentage of samples. With replacement concept, I can construct multiple bags. So now with say if I construct n different bags of data, n different subset of data from this 1000 samples, so obviously for each and every subset of the data, I can construct one decision tree. I can construct one decision tree. So 10 decision tree that I can construct by saying this row sampling, say B1, B2, B3, so on up to B10. So using this 10 bags, I can construct 10 decision tree. DT1, DT2, DT3, so on DT10. So 10 decision tree. Now I'm just going to ensemble this 10 decision tree result. How to ensemble this 10 decision tree result? Say my decision tree 1 is telling that it belongs to Cancer, and decision tree 2 is telling that it is also belongs to Cancer, and decision 3 is telling that it belongs to Cancer. Say decision tree 10 is telling that it belongs to non-Cancer, and I'm just going to count how many Cancer and how many non-cancerous decisions are made by this 10 decision tree. For example, say 7 decision trees are telling that it is belongs to Cancer, and 3 decision trees are telling that the test sample is belongs to non-Cancer. Then I will go by the max vote opinion or majority opinion. The majority opinion is saying that 7 belongs to Cancer. So my final decision like is it noise from my side?
I'm not sure, sir. I think somebody, yeah, I think now it's gone, sir.
Yeah. So out of this 10 with respect to this 10 decision tree that I have derived from 10 back of data, 7 decision trees are telling that it belongs to Cancer, and 3 decision trees are telling that it belongs to non-Cancer. So obviously my final decision about the test sample is that test sample of data is actually belongs to cancerous case. So this is how bagging works. So even though this I'm explaining under random forest, up to this step, if we do only this step to make the classification decision, then it is known as bagging. Now, how random forests differ, or what is the extra thing that random forests have? That randomness that we are bringing into random forest, not only by doing the row sampling, we are also doing the column sampling. Right? So here itself, row sampling with replacement and column sampling. What is meant by column sampling? So here, previously, while I'm saying B1, B2, B3, so on, B10, that each and every bag is having some subset of rows, right? So in total, I have 1000 rows. Now in bag 1, I'm just going to have 600 rows. Say, for example, in bag 1, the data set size is 600 cross 10. Here also it is 600 cross 10. Here also it is 600 cross 10. Here also it is 600 cross 10, like that, right? So now even after doing the column sampling, this is 600 cross 10, 600 cross 10, 600 cross 10 is with respect to only row sampling. If you are doing column sampling also, then obviously this will be like 600. Let me write here. 600 cross 4, 600 cross 4, 600 cross 4, and 600 cross 4. Right? So like this, right? So if you are doing the column sampling also, then obviously we are actually selectively choosing some of the features. So previously we have actually chosen only the rows, selectively some rows. In column sampling, we are selectively choosing some columns. We are not actually using all the columns. So that is how your random forest is differ from your bagging. So if we bring the randomness both in row and column, then it's become random forest. So apart from that, building the decision tree and taking that max vote decision, all the remaining things are same, right? So just give me a 1 minute. I will close my window. Some bird sound I keep on hearing. Yeah, sorry for that interruption. Fine. So this is how both row sampling and column sampling is actually getting applied in random forest to make the classification decision, right? So the key point that you have to keep in your mind before going into boosting is each and every decision tree that we have constructed in our random forest or bagging are independent to each other, which means the decision tree 1 is actually completely independent, or it doesn't have any kind of relation with DT2, right? And also DT3, it doesn't have any kind of relation with the other decision trees. So each and every decision trees are highly independent. It's clear. It is completely independent. Rather than saying highly independent, it is completely independent. It doesn't actually do any kind of alteration in forming one decision tree with respect to other decision tree result. So each and every decision tree results are actually completely independent. Each and every decision tree is actually taking its own decision from the subset of the data. It is not actually seeing what other decision tree is telling, what other decision tree is result is. Based upon that, it is not actually making any decision. So this is one important characteristics of random forest, which is not there in our boosting. So in boosting, basically a kind of one line, one tagline I generally use to tell for boosting is an algorithm which will learn from the mistake. Boosting is the algorithm which will learn from the mistake, right? So
this
learn
4 is the fixed, or again in column sampling also randomly 4 different columns taken for each decision tree.
yeah. So you are asking how this 4 comes, right? So this is also kind
it the
of
same
random.
4? Is it the same 4 columns or
No,
different feature?
random, say like that 600 rows randomly it is taking. No, similarly out of the 10 feature, randomly for each and every decision tree, randomly will pick any 4 feature.
Okay.
Right. Say sometimes that 4 feature maybe and maybe not a powerful feature also, but still it is actually randomly picks that. Anyway, it is an ensembling decision at the end. It is not going to take the decision with respect to one decision tree alone, right? So that is the kind of idea. We want to bring more genericness in our model. I don't want to strictly take the decision always with respect to some set of feature. I'm just using all the features randomly in a different combination to make the classification decision. So that is the kind of idea here in column sampling. How it is 4? Why it is 4? Why it is 4? So this is like a random choice. You can play with this is an hyperparameter. You can randomly pick 5 feature, you can randomly pick 4 feature, you can randomly pick 6 feature, but more the feature that you fix, the randomness will reduce, right? So if there are only 10 feature and you are picking 8 feature always for constructing each and every decision tree, if you are picking 8 feature, then the concept of randomness itself, it's not there, right? So almost 80% of the feature that you are choosing, in the sense the genericness is not there. My model is actually making the decision by using all the 8 features. So I want my model to just try to make the decision with respect to some random feature. Then out of that randomness, the genericness of the model is more, as my generalization of the model is more, in the sense my model ability to handling the overfitting nature is more. That is a kind of idea. And also in sklearn, we have the function like log, square root. So we have discussed that max feature. For max feature hyperparameter, we can use the log2 method, square root method. If you are using square root method, and say if you are having 12 features in your 12 input features in your data set, and if you are using the square root method of column sampling, then square root of 12 it will take. So square root of 12 is 3 point something. So it will round off to 4. So 12 feature is there, and if you are using the square root method for choosing the 4 feature, then choosing some feature, then it will choose only 4 features, because square root of 12 is 4. But randomly it will choose the 4 features in each and every bag. Right? So once we bring this randomness through columns and rows, each and every decision trees are completely independent of each other. Whereas in boosting, each and every decision tree in boosting also we are going to construct multiple decision tree. In some variants of boosting, it may not be only decision tree, it may be some other base learner also. But each and every this base learner in boosting is have some kind of dependency. That is the first point, how your boosting is differ from your bagging or your random forest. In bagging or in random forest, all the individual learners are completely independent of each other, whereas in boosting, these learners are sequential. Which means first I'm just going to construct one decision tree, one base learner. Then based upon the output of the base learner, based upon the output of the decision tree, I'm just going to decide in what way I need to construct the second decision tree, or in what way I'm just going to construct the second base learner. So that is the reason why these boosting models are known as sequential model. This is not independent of each other. Each and every decision tree or each and every base learner is not independent of each other. It's dependent on each other. It is dependent on each other. Each and every base learner in boosting algorithms are dependent on each other. What is mean by dependent on each other? First, we will construct one base learner, one decision tree. We will see what is its output. Based upon its output, how to improve the model, we will think, or we will do some kind of mathematical process for it. And based upon that, we will construct the next decision tree or the next base learner. So that is why it is known as learn from the mistake. First, I'm just constructing one base learner and I'm seeing the output, and I come to know to what extent my model is actually predicting the output and to what extent my model is making the mistake. Then from that, to avoid those mistakes, to avoid those misclassification that has been carried out by your first level of your boosting, I will be framing the second level. Based upon the mistake which has been carried out by your first base learner, I'm just doing some modification in my model on the data. So I'm just constructing my second level of base learner. So that is the reason why boosting algorithms are known as learning from the mistake, right? So this is one very good effective way of training your model, because even we humans used to get good experience in our domain only by learning from the mistake, right? So even I used to tell, like while I'm doing some Python session and other things, so I asked my students to just go through the error report, right? So Python generally used to print a big error summary, right? So that is actually, it is explaining what is our mistake. So once we just let that error happen, and if we go through that error, why this error happened, then obviously we will be in the position to understand how to use that function, right? So our learnability will be very high if we learn from the mistake, if we learn from the error. So that is what your boosting is exactly is doing. So with respect to the first base learner, it is actually building your model, and once it builds the model, it analyzes its output, and it is actually spending time, or it is actually understanding the mistakes or incorrect classification, and based upon the understanding that it had with respect to the incorrect classification, it is actually constructing the second level base learner in our model. So sequentially, then with respect to the second learner, how many observations are correctly classified, how many observations are wrongly classified. Once again, it's giving more importance for that wrongly classified samples in order to understand it further. So the third weak learner will now build it with an objective of learning about the wrong classified sample of the previous weak learner. Like that, sequentially you can construct so many base learner, such that each and every base learner will try to learn something about the previous mistake, so that it will just try to avoid those mistakes which has been carried out by your previous weak learner. So in this process, after 5 level or 7 level or 9 level, so on, right? It's based upon the data complexity. So at what point of time you are actually getting the correct output as per your client requirement, at that place you can stop. So that is the idea of boosting. So it is actually sequential learner. So it is also learning from the mistake. So how it is actually exactly doing that, we are going to discuss in detail by seeing its math, how there are different variants of boosting like ADA boost, gradient boost, XG boost, CAD boost, light GBM boost, and all those things. But basically in today's session, we are going to discuss the math of ADA boost and gradient boost in detail. The other boostings are variants of your gradient boosting only in terms of optimization, right? So extreme gradient boost is nothing but how to, the base concept is gradient boost only, but in terms of optimization, in terms of utilizing the resources, or in terms of doing the same operation in a quick way, they have slightly modified some of the mathematical part. Of course, it is like a kind of, say, I used it to solve some problem in a traditional way. Someone can use some kind of shortcut to do that problem in a very quick way, right? So likewise, only that other variants of gradient boosting is differ from the base gradient boosting. So mathematical logic of all the gradient boosting is almost same. Of course, how effectively, how quickly we can do those computation, in that aspect only the other boosting algorithms are different from the gradient boosting, right? So but ADA boost mathematics and gradient boost mathematics are kind of different. We are going to see these two mathematics in detail, how ADA boost works with respect to some toy data, as we usually do always. I'm just going to take one 5 rows, 6 rows data, and with respect to that 5 row, 6 row data, how ADA boost is making the classification result. Then we will be doing the same thing with respect to gradient boosting. So once you understand this ADA boost concept and gradient boost concept, then we can jump into Jupyter Notebook to execute different variants of boosting and how it is actually improving the performance, and all those things we are going to discuss, right? So basically a tagline is boosting is an algorithm which is learned from the mistake. Now let me discuss the first variant of boosting, which is nothing but ADA boost. So what I can do is, rather than typing, I have already worked out one problem. Let me share that, and I will take you step by step of that mathematical solution. Right, so this is one sample data. So it is having 4 columns of data. So the first column is chest pain, blocked artery, patient weight, and heart disease. So heart disease is an output column. So our objective is predict the heart disease based upon chest pain, blocked artery, and patient weight, right? So chest pain and blocked artery are categorical column, whereas patient weight is an continuous numerical column. So using these 3 information, we are going to predict the heart disease. I hope everyone have the clear idea on how to do this task with respect to logistic regression, not in terms of SQL programming point of view. In mathematical point of view, if one such a toy data set is given to you, how logistic regression works, how can I frame those mathematical equation, how decision tree works, how can I construct the decision tree with the Gini and all those things, how KNN works for this, how naive Bayes work for this, and how bagging work for this, how random forest work for this. That kind of mathematical understanding you should have. I hope that you have that mathematical understanding with respect to all the different algorithms that we have discussed. Now in today's session, we are going to approach this toy data set through ADA boost math, right? So always your ADA boost algorithm start from the concept called weak learner, right? So the base learner, I told no, in a random forest, there are so many base learners. The base learners are actually your decision tree, right? So similarly in ADA boost also, there are so many base learner. We are going to call those base learner in ADA boost as a weak learner, right? So the base learner in ADA boost is known as weak learner. So what is mean by weak learner? If you see in random forest, randomly we are taking some sample and randomly we are taking some columns, and with respect to that we are actually building the complete decision tree. Of course, if you can by using the max depth and other minimum sample split and all those things, you can actually do the pruning. But still, conceptually speaking, for that subset of data with random sample and random columns, it is actually building the decision tree, a grown decision tree, right? So even though it's not completely grown decision tree, provided that if you are using max depth and minimum sample split, those hyperparameters, still it is a kind of grown decision tree. Whereas in AdaBoost, the base learner is actually known as weak learner. What does mean by weak learner? What does mean by weak learner? So weak learner in terms of decision tree, is a decision tree with only one root node. Decision tree with only one root node. So which means our decision tree with only one depth. Decision tree with only one depth is like this, right? Say I'm just making some decision with respect to, say here in this case we have weight. So weight greater than 176. If weight is greater than 176, how many are having the heart disease? How many are having the heart disease? How many are not having the heart disease? How many NHD and how many HD? Here how many HD and how many NHD? So we are straight away calculating this. We are straight away making this decision. It is like, even though I have n number of input features, now I am making the decision. About the output using any one feature alone. So obviously the decision is not actually very trustable decision, right? Yes or no? So I'm just teaching you machine learning. I'm just teaching only one algorithm. With that algorithm, if I ask you to build the predictive model, you learn something. You learn that one particular algorithm, but it is not the end, right? So whatever the predictive model that you are building may not be an optimal model if you know only one machine learning model. So you have to apply different machine learning model, and with respect to the different machine learning model, which model is producing the better performance, that you have to give us a final model to your client. So similarly here there are so many input features. So I need to take the decision about my output by utilizing all those input features in some way, right? But a weak learner is the one which actually make the decision with respect to only one input feature. Here in this case, a decision tree with max depth equal to 1. What is the meaning of that? It taking the decision about the output using only one feature here, say weight. If weight is greater than 176, whether they are having the heart disease or not. If weight is less than 176, what is the chance that they are having the heart disease? Say while I'm printing like this, say the heart disease cases are 10 and NHD cases are 5, and say here the heart disease cases are 3 and the NHD cases are 7. What is the meaning of this? What is the probability that your test sample belongs to heart disease with respect to this leaf node? With respect to this leaf node, what is the probability that your test sample belongs to heart disease?
10 by 176.
176, how it is? 176 is the some threshold. Weight is greater than 176.
10 by 15.
10 by 15.
10 divided by 15. Similarly, non-heart disease, 5 divided by 15. So obviously this 10 divided by 15 value is more, no?
Sir, you asked out of with respect to left leaf node or with respect to whole, sir?
With respect to this node.
Okay.
Right. In this node, say after splitting with respect to this condition, totally 15 samples are coming here, 10 samples are going here. So initially there are totally 25 samples. Out of the 25 samples, 15 samples are coming here and 10 samples are going here after making the condition with respect to this weight 176. Then out of this 15 sample, 10 are belongs to heart disease and 5 are belongs to non-heart disease in the sense. this node have more probability with respect to the hard disease. So whenever one test samples reach this node, I will tell that that person is having the hard disease. Yes or no? That is the idea, right? Even though it is not pure, if I want to make some decision with respect to this level of decision tree, if one test sample is coming, and it's reaching this node, say if anyone weight is 190, one person weight is 190, then obviously I will tell that the chance for him to get heart disease is more, because with respect to this trained decision tree, whenever greater than 176, out of this 15 people, 10 people are having the heart disease. So which means the probability that person to have the heart disease is more when the weight is greater than 176. So similarly here, if you see, it is actually the chance for heart disease is 3 divided by 10 and chance for non-heart disease is 7 divided by 10. Right? So obviously here this value is more. 7 divided by 10 is more. So this leaf node is kind of non-heart disease node, and this node is actually a kind of heart disease node, because heart disease probability is more here in this leaf, whereas non-heart disease probability is more in this leaf. But obviously I can't make this decision in a very concrete way, because there are so many out of this 15 sample. Here still 5 samples which is actually belongs to non-heart disease case. Here there are 3 samples, still it is actually belongs to heart disease case. So I can't simply make the decision, or even if I make the decision like whenever the person weight is greater than 176, they are having cancer, and they are having heart disease. When the person weight is less than 176, they are not having heart disease. If I make that decision may tend to have an error, right? So because here 5 cases are non-heart disease cases are there. So whenever my test input is reaching this node, I'm making the decision like he is having heart disease, but there may be a chance, reasonable chance, 5 divided by 15 chance is there for that person to not having the heart disease. Similarly, whenever a person's weight is less than 176, I'm just going to make the decision as he is not having the heart disease, but still it is tend to have an error, because 3 divided by 10 chances there that person with weight less than 176 can have heart disease. So with weak learner, obviously we can't able to make a very good prediction, because weak learner is making this decision with respect to only one root node, only with respect to weight. I'm just making this decision, right? So as in complete decision tree, what we will do here, it is not completely homogeneous. So I will split this node further. Using some other input feature or some other threshold for weight or some other input features. I will keep on split it further until I'm getting the root node, leaf node characteristics like more homogeneous in nature, right? But with respect to weak learner, with respect to only one root node, obviously I can expect lot of misclassification to happen. Yes or no? So it is like now in this class there are 50 students, right? So I'm just doing only one session for machine learning. Then after that I'm just conducting some test. So in that one session itself, so many algorithm I taught to you people. So at the end of doing that one session, I'm just conducting some tests to you, right? So it doesn't give the guarantee, right? Like everyone will do well in that test, because I have done only one session, right? In that I have, of course, just like that, given all the input, which means I have taught you all those algorithms. But you may not actually properly train with those algorithms. You are not properly learn all those algorithms, because I have not done my teaching in a detailed way. So just in one session, just in 3 hours, I just dumped all those information to you, right? So it is not optimum for everyone to learn all those concepts correctly. So while I'm doing some tests for you, some of you may not score well, but even though I have taught you only all those algorithms in one class, some of the students may understand all those things very clearly, right? Some of the students may understand all those things very clearly. In the test, they may really do well. But some of the samples, some of the students may not understand the things well, so they may not score well. So what I need to do, okay, these are all the set of students, they are not actually done well. So while I'm doing the next session, I'm just giving the more importance to those students. So whoever the student who already understand the concept well with respect to my first lecture itself, I'm not really concentrating more on those fellows. I'm just concentrating more on people who having some difficulty in understanding the concepts at the end of my first session. So I'm just giving focus more on those set of students. I'm just making sure these set of students is learning well during my second session. So that is what. So first, that is actually that is how actually boosting works. So I'm just doing only one session. No, that is actually weak learner. Properly in complete decision tree, what I will do, I will complete decision tree concept is like I'm just doing 6 sessions or 8 sessions in a stretch, and at the end I'm just making sure whether you learned properly or not. In boosting, what I'm doing, I'm just doing one session. After doing just one session, in one session itself, I try to give all those inputs to you, and at the end of one session, I understood like who are all learned well, who are all not learned well. Then while I'm doing the second session, I'm just giving more importance to the students who are not really learned well at the end of my first session. So weak learner will here the boosting will work in the same way. I'm just making some decision with respect to only one input feature. With respect to one input feature, weight, say if you have 1,000 patient in my data set, for all the 1,000 patient, I'm just taking the weight column alone. With respect to that weight column alone, I'm making the decision. I may not actually take the come up with the correct decision because I'm using only weight. But using weight itself for some observation, I can correctly find whether the person is having heart disease or not. So it means for those samples, weight itself a kind of indicator through which I can make the decision. So I won't give more focus on those samples for which weight itself is enough to make the correct classification decision. Whereas what are all the observations for which I can't take the decision I can't take the correct decision with respect to just weight. Here, totally how many cases for which I can't take the correct decision with respect to weight? In the sample data that I have displaying you on screen, out of the 25 observations, 15 observations are coming on the right side and 10 observations going on the left side. So here, totally how many misclassifications? Can anyone tell? How many misclassifications? How many misclassification in this decision tree?
5.
So here I'm telling like this node is for heart disease and this node is for non-heart disease, because heart disease count is more compared to non-heart disease. So I'm just whenever my data comes here to this node, I'm making the decision like the person is having heart disease. Whenever the flow is coming into this leaf, I'm making the decision like the person is not having heart disease. With respect to that, with respect to this, as this belongs to heart disease, there are 5 cases which is non-heart disease here. So this is actually misclassified samples. Here totally how many misclassified sample? 3 misclassified sample, right? So totally there are 8 misclassified sample. So out of this 25 sample, if I use weight as an input feature, only weight as an feature, and I'm making the classification decision, in total 17 decisions are actually going right and 8 decisions are going wrong. So now while I'm constructing the next level learner, that is next weak learner, so after understanding this, like which are all the samples correctly classified, which are the samples wrongly classified, I'm just going to construct the second weak learner, right? Weak learner 2. So in this weak learner, I'm just going to give more importance for this 8 samples. In the second weak learner, I'm just going to give the more importance for this 8 samples. So I'm just importance means I just frame one new bag of data. I'm just going to frame one new data in which the representation from this misclassified sample will be more. Like in my second session, I'm keep on asking some questions to the people who not able to understand the concepts of my previous session. So I'm just giving more importance. I'm just keep on asking, I'm just keep on discussing, I'm just keep on interacting with the set of students who couldn't able to understand from my first lecture. So I just make sure that they are understanding, right? They are understanding the concept that I'm telling in the second lecture. So that is the kind of idea. So when I'm forming the second week learner, I'm just giving more importance to this misclassified samples, to this 8 samples. I'm just giving the more importance. How to give the more importance? What is meant by more importance? All those things we are going to discuss now with that mathematical workout. But this is how a boosting works. It will just construct one weak learner. Weak learner with respect to decision tree is nothing but a learner or a decision tree with max depth equal to 1. And with respect to that poor model, everyone agreeing that, right? So if I make final decision with respect to only one feature, obviously it could be a kind of poor model, right? Yes or no?
Yeah.
Unless otherwise the Gini value for that one particular feature is 0. If Gini value for this particular feature is for this weight is 0, when weight greater than 176, if the Gini value is 0, completely 0, then obviously it will produce 100% accuracy. It's produced a very good result. But in dataset we can't have such a kind of features. If we have such a kind of feature, one feature with Gini value equal to 0, then obviously we don't need machine learning model for it. Right? I can simply take the decision. Okay, your weight is greater than 176 levels. Fine. You will be having the odd disease. If your weight is less than 176, you don't need to worry. You don't have odd disease. So for that purpose, we don't want machine learning model at all. Right? So, but anyway, some kind of learning your machine will get with respect to that one single feature. So like that, we are actually sequencing the different weak learner in a sequential way so that we are achieving the correct output, right? So in the second week, while we construct the second week learner, some other feature will be considered as the root node. So here weight has been considered as the root node, no? So in the second week learner, with respect to that new data set that we have formed, with respect to that new data set we have formed, by giving more importance to this misclassification, we will be computing this Gini and other things, and we are choosing the correct root node. With respect to that root node, once again we are actually forming this max depth equal to 1 decision tree. Then with respect to that, we are seeing how many are correctly classified, how many are wrongly classified. So we are going to stop this process once almost all the samples are correctly classified. So this is how your boosting works. That is the reason why it is actually known as learning from the mistake. So why mistake is happening? Because the mistake is happening because the first base learner is not a complete grown algorithm. It is a weak learner. It's with only few features. It is actually making the final decision. So obviously we will expect so many mistakes. So with respect to that mistakes, we are learning and we are actually modifying our data, and we are understanding who are all the students who is really understanding or we are really doing well, and who are all the students who is struggling. That we are understanding by just teaching one session itself and just getting that list of students. Then with respect to that list of students, I'm just altering my way of delivery, or I'm just giving more importance to some set of students, so that I'm just making sure that they are actually learning properly in the correct direction.
Yes,
Right?
Sir,
Yeah.
I have a few questions.
Yes. Yeah.
So you're saying this boosting works with stamp, right?
Boosting what with?
Stamp. Like
Stump. Yeah, decision stump.
Yeah, decision stamps, right?
Yes.
And how the sampling works here? It's a with replacement or?
Here it is not row sampling. The thing, the whole data we will be passing. The whole data we will be passing with respect to this only one condition. Say I have 10 features in my model. I'm just going to pick only one feature. With that one feature, I'm just applying all my data. It is not row sampling, column sampling concept and all here. Always I'm just going to, with respect to max depth equal to 1 as my weak learner, always I'm just going to pick only one feature. Then with respect to that one feature, I'm just going to construct one decision tree. So obviously it is a decision stump. In that decision stump, I'm applying all my data. So some of the data will be correctly classified and some of the data will wrongly classified. Then with respect to that wrongly classified data, I'm just coming up with another new data set. So this that new data set that I'm going to get from the wrongly classified sample, you can't call that as a row sampling. So I will be telling you while I'm teaching you that math behind it, how we are going to derive or how we are going to get that new data set or new bag of data from this misclassified sample. We are going to discuss now, but it is not like randomly we are picking some samples, right? So that is for random forest. Here in boosting, that bootstrapping we are not doing. We are not actually doing the row sampling and column sampling. Here after choosing one feature for your root node, we are applying all the data. If in your data set, if you have 1000 data, all the in your train data, if you have 1000 observation, all the 1000 observations that I'm applying in my first week learner, and I'm just seeing how many are correctly classified, how many are wrongly classified. With respect to that wrongly classified, once again I'm just forming that 1000 data. How it is possible once again to construct the 1000 data with that wrongly classified sample, that we are going to discuss now. But it is not like randomly picking some subset of the data.
Okay. Then I hope we'll also cover that how this decision weak learners makes the decision, right?
Yes, of course. We are going to do this now. Right. So I just given the overall idea about boosting, how step by step it is evolving. Now, while I'm explaining that process with respect to this toy data, we will be knowing like how that first level of data set decisions will be made, and with respect to that misclassification sample, how the new data set will be formed. All those things we are going to explain now with respect to this toy data set. Before that, only one more point I want to tell. This weak learner need not to be always a decision tree with a max depth equal to 1. Sometimes people will take even max depth equal to 2, because with 2 feature, whatever the things the model is learning, that also tend to have a lot of misclassified sample, right? So typically max depth equal to 1 will be the better choice, or maximum you can go even up to max depth equal to 2. Going more than that, it is not preferable, because if you use max depth equal to very high, then obviously it is not actually making so many mistakes. So because as it is having more features to make the decision, obviously it won't make much of mistakes. So your model will become a kind of overfit model. Your boosting will become a kind of overfit model if you use the weak learner with so many features, right? So typically it is max depth equal to 1. In some cases, people will go with max depth equal to 2 also, but not really more than that with respect to this AdaBoost that we are talking about now. And also, rather than using the decision tree, you can also use logistic regression. Can anyone tell with respect to logistic regression, what could be the weak learner? With respect to logistic regression, what could be the weak learner?
Single variable.
Yeah, so we know that that logistic regression or linear regression have this base equation like b1 x1 plus b2 x2 plus b3 x3 plus b0. Using this, we will be calculating the probabilities so that it's become logistic regression. Otherwise, this simple equation is actually linear regression. So with respect to linear regression or logistic regression, the weak learner is any one feature. Say if you are taking only x2, then b2 x2 plus b0 is the weak learner. Yes or no? b2 x2 plus b0 is actually weak learner, right? Because I'm making the decision with respect to only x2. Actually, I have to take the decision with respect to x1, x2, and x3 so that it's a complete learner. It's a complete model. Now, if I'm making the decision, what is y by using only x2, by simply multiplying b2 x2 plus b0, it may not be a complete model, right? So it's a weak learner. So x2 will have some kind of contribution towards the output, but it is not. It's not that full contribution on output comes by only x2. So obviously your model tend to have more error if you just build your model with respect to only one feature. So this is how the weak learner construction can be possible through your linear models also. But generally, throughout all those ensembling process, we are going to use the decision stump. Decision stump only as a weak learner. Decision stump is nothing but a decision tree with max depth equal to 1. But in a customized way, if you want to write, you can also use logistic regression with one feature or linear regression with one feature to construct your weak learner. Now let us discuss whatever the thing that we have that I have told. Now I'm going to demonstrate mathematically on this data set.
So 1 second.
Yeah.
So that means the weak learner was weight variable in the previous slide which you showed.
Weak variable.
I mean weak learner. That means it's weight feature.
Yeah, here.
Weight feature is the weak learner.
Yeah, only with weight feature, if you are actually constructing the model, then this whole model is actually weak learner. This whole thing is actually weak learner.
Okay, so that means for a weak learner too, will it be the same feature or different feature?
Say how I am getting this weight, it is based upon the original data set. For that original data set, I'm just computing Gini for each and every column, and which column Gini is actually less, that I'm just going to consider as the first feature in my first weak learner. Then after doing this process, I told no, I will modify the data. Okay. Yes or no?
Yes.
Right. So with that modified data, once again, I will do the Gini impurity calculation, and for which feature my Gini impurity is less, I will analyze that, and that I will be using as the root node for my second weak learner.
Okay, sir. Got it.
Just hold on. Just hold on. So I'm going to explain all those things now with respect to this thing. Right. So now here we have chest pain, blocked artery, patient weight, and using this three feature, I'm just going to predict whether the person is having heart disease or not. So initially in Adabu's algorithm, I'm just going to give equal weightage for all my samples. So while I'm doing the very first session, I don't have any idea like who is the bright student, who is the weak student, for which student I have to give more input, for which student I have to keep on ask something so that I can make him to learn properly. No idea I'm having while I'm starting my first session for the one new batch. So I'm just giving the equal weight for all the students. Here, like the same for all the observation, I'm just giving the equal weight 1/8, 1/8, 1/8, 1/8. So I don't know which observation has been correctly classified or which observation may wrongly classified. So because I have not built anything, so here only I am just going to make my model to learn on this data. So at this point, I'm just giving equal weight for all the samples, right? So why 1/8? Because in this data set there are totally 8 samples are there. So there are 1/8, 1/8, 1/8. So that initial sample weight is actually 1/n, where n is the total number of samples. So once I have assigned the equal weights for all those samples, I'm just going to compute Gini index for each and every feature. So you already know how to find the Gini impurity for categorical column and how to find the Gini impurity for numerical column. But anyway, in sklearn, we are not going to do it. But anyway, so that mathematics is going to apply on each and every column. So we have discussed that the Gini impurity formula is 1 minus summation of probability I, pi the whole square, where I is different classes. So here there is 2 classes that we need to compute whether the person is having heart disease or not. So now with respect to chest pain, I'm just computing this Gini. When chest pain is yes, under heart disease, there are three occasions where heart disease is also yes. There are 2 occasions where heart disease is actually no, right? Say if I am making the decision like if person is having chest pain, then he is having heart disease. If I'm making such a kind of decision, obviously at 3 occasions it may be correct, at 2 occasions it may be wrong, because here in this data set, whenever the chest pain is yes, the heart disease is yes at the 3 occasions, and you can see these 2 occasions when chest pain is yes, the heart disease is still no. The heart disease is still no. So which means under here there is 3 occasions where heart disease is yes when chest pain is yes. So I'm just making that as a kind of correct decision. And when chest pain is yes, at 2 occasions that heart disease is no. So that is actually kind of incorrect decision, provided that this node I'm just allotting for hard disease. If I'm allotting this for hard disease, whenever the chest pain is yes, in 3 occasions the person is having hard disease, so it's a correct decision. But in 2 occasions, even though the chest pain is yes, the person is not having the hard disease, so that is an incorrect decision, as we discussed just before with respect to weight. Similarly, whenever the chest pain is no, there are 2 cases where the patient is not having heart disease. So chest pain is no heart disease. So that is a correct decision. When chest pain is no, he is not having any chest pain, but still he is having heart disease, right? So if I make the decision like, okay, you are not having chest pain, so you don't have any chance to get the heart disease. If I make such a kind of decision, it may have a tendency to get some error, because there is one sample or one person who is not actually having the chest pain, but still he is having heart disease. So with respect to this chest pain, if I compute the Gini, we have already discussed how to find the Gini. 1 minus, so while I'm computing the Gini for chest pain, in chest pain there are 2 levels, chest pain equal to yes and chest pain equal to no. So I have to find Gini for chest pain equal to yes and chest pain equal to no. And the weighted sum of yes and no is nothing but the overall Gini for the chest pain. So we have already discussed that during our decision tree. So I'm just applying those equations, and I'm just getting the Gini impurity value as 0.46. Similarly for blocked artery, once again I'm doing this calculation and I'm getting the Gini value as 0.5. And for weight greater than 176, I'm getting the Gini value of 0.2.
Sir,
Now, yes.
When you say blocked arteries, it is nothing but weak learner 2, is it?
No. So now I'm in the process of identifying the first weak learner. So in order to identify the first weak learner, I have 3 input feature, chest pain, blocked artery, and weight. So out of these 3 input feature, which feature I have to use to construct my first weak learner? That is my objective. For that, I'm just finding the Gini value for each and every input feature. Now for the chest pain, I'm just getting the Gini value of 0.46. For blocked artery, I'm getting the Gini value of 0.5. And for weight, I'm just getting the Gini value of 0.2. Got the point?
Yes, sir. Got it.
Yeah. Now, out of this 3 feature, which feature is having the least Gini?
0.2.
0.2. So using this weight as my feature, I'm going to construct my first weak learner. Got the point? So I'm just going to use weight, and I'm just going to construct my first weak learner. So now this is actually my first weak learner.
One question here, sir. Weight is continuous variable, right? So did we just take 176? It's just
of course.
Or we should consider a more number of values, iterate through.
Exactly. So my focus, just to explain this boosting, we have already discussed this. If it is a continuous, how to find this threshold? Here I have used the threshold as 176, but we have discussed in class, and also I have worked out in one Word file, and I have shared that with you, right? You have to do the moving average. If you remember, for some I think some finance data, simple finance data, written volume, something like that. For that, I have done that calculation. So you have to just ascend your continuous values, ascend or descend, and you have to do the moving average. And for each and every moving average threshold, you have to find the Gini. And for which moving average threshold your Gini is less, that you have to consider as the threshold for that particular continuous numeric feature.
Okay, sure.
Right. So I have not done that part, but anyway, say 176 is that value. After doing some analysis, you understood, like for 176 is the out of all the values which weight is having, using this 176, which will give the least Gini, fine. But you have to make sure that whether that Gini is actually more or less compared to the other feature. Here the other features are blocked artery and chest pain. Compared to this Gini, when I choose weight value greater than 176, I'm getting the Gini which is actually much less than the other. So I'm just going to consider this weight greater than 176 as my root node. So using this weight greater than 176, we are actually,
So you are taking least Gini.
Right? Least Gini impurity.
What would be the condition if I am using entropy?
Yeah, see, while you are using entropy, internally that calculation will be happen in terms of information gain. Using entropy, we will be calculating information gain. So if you are making the decision with respect to the plain entropy, then entropy also should be minimum. Entropy also should be minimum. But generally in SQL and in other in mathematics, from entropy people will calculate, because overall entropy minus that particular feature entropy, like that they have framed that equation. So once you have that equation, then it become information gain, right? Even though in sklearn the keyword that we are using there is entropy, but internally it will compute the information gain, because information gain is actually derived from the entropy only. So if you are expressing in terms of information gain, then you have to look for the feature which is having the high information gain.
Yeah.
You got the point?
Yes.
But conceptually, if you see just entropy should be less for the homogeneous feature. Entropy should be less for the homogeneous feature. So lesser the entropy, then it means that that feature is homogeneous, so that you can use. But in decision tree construction in sklearn, that entropy concept has been written in terms of information gain. So it is like you are subtracting that entropy from 1, right? Whatever the entropy value that you are getting, you are subtracting from 1, in the sense, say lesser the entropy, model is homogeneous. But if you are subtracting 1 minus entropy, then what happens? The value will become high, no?
Yeah.
So which means in terms of information gain, you should have the high value of information gain. So just keep in like this, entropy and information gain are actually inversely proportional to each other, but both are talking about the same thing only. But these two are inversely proportional to each other. So if you are defining something with respect to information gain, then which feature is having the high information gain, that should be your root node. Fine. So now with respect to this weight greater than 176, we are actually making say whenever the weight greater than 176 is X, 3 cases are correctly classified, which means 3 cases whenever weight is greater than 176, in this data set, only in 3 instances or in 3 places the weight is greater than 176. In all the 3 places, the person is also having the heart disease, yes, heart disease. And in 5 places, the weight is less than 176. In 5 places, the weight is less than 176. Out of those 5 places, 4 places is not having heart disease, and in 1 place, even though his weight is less than 176, that person is having the heart disease. That person is having the heart disease. So, which means there is one incorrect classification. There is one incorrect classification. So I have to model this incorrect classification. I'm just going to give you the formula. I'm not going to take you through the derivations of all those formula, because that really don't need. But anyway, if you are interested, you can go through some literature to understand how they are derived, all those formulas. So now the total error by this weak learner. We initially, if you remember, what is the kind of weight that we have given for each and every sample? What is the weight for each and every sample?
1 by 8.
1 by 8. So here, totally how many incorrectly classified sample? Only one incorrectly classified sample. So the total error is 1 into 1 by 8. 1 into 1 by 8. So total error of this weak learner is actually 1 by 8, because there is only one sample which is actually incorrectly classified. If it is 2 samples in total, whether here or here, under this any one of those leaf, if there is incorrect classifications are there, we have to cumulate all those things and we have to multiply that with the sample weight. Here there is only one incorrect sample, so 1 into 1 by 8 is nothing but your total error produced by this weak learner. Weight of the total error produced by this weak learner is actually 1 by 8. Now from this, I have to compute something called amount of say. What is this amount of say? Basically, just try to keep this in your mind. Amount of say is a measure which talks about the reliability of this particular weak learner. To what extent you can really trust this weak learner. So that has been modeled through this mathematical function, amount of say, right? So to what extent I can trust this? To what extent I can give importance to this particular weak learner while I'm making the decision. So that has been given by the amount of say. So this amount of say is actually 1 by 2 ln of 1 minus total error divided by total error. So we have total error value now. So the total error value is 1 by 8. So if you substitute in this formula, I'm just getting the 0.97. So 0.97 is the amount of say for this particular weak learner. Say while I'm calculating, while I'm just working, constructing some other weak learner, for some other weak learner, if I'm getting the amount of say as 2.5, then which means that second weak learner or the other weak learner whose amount of say is 2.5, which is actually more trustable than this first weak learner, more trustable than this first weak learner. So the first weak learner result is actually not much trustable because that amount of say is less, whereas some other weak learner amount of say is more than this weak learner, then that weak learner is much more trustable, right? So amount of say will actually tells you to what extent you can trust this. You can trust this. You are while you are asking some opinion, each and every one of your friend will tell their own, will tell some opinion, so that you can use their opinion to take your decisions. But you will be giving some more importance to some of your close friend opinion. At the same time, you are not giving that much importance to some of your far friend opinion, right? So like that. So for which weak learner it need to give more importance, for which weak learner it need to give less importance, that has been given by this amount of say, right? So once I have computed the amount of say, I have to, now I'm just coming into the process of constructing the new data set, constructing the new data, new bag of data or new data set, new version of the data set from the learning that I have achieved from the first week learner. So how to do it? I have to modify the sample weight because, as I told initially, while I'm starting this session, I don't know anything about my student. So each and every student is same for me. Now, after I'm conducting some tests to them, after I'm teaching something to them, and after I'm evaluating them based upon what I taught them, now based upon their performance, I know, okay, these are the students understanding my delivery. These are the students are not understanding my delivery. So I have to do something extra to make these students also to understand my delivery. So that is what now I'm just giving. So which means for the misclassified samples, I have to give more weight. Yes or no? Initially, I have given the equal weight for all the sample. Now for the misclassified sample, I have to give more weight. I have to give more focus on that misclassified sample. Whereas the correctly classified samples, well and good. Yeah, whatever that I have delivered, that itself is enough for them to understand. Whatever that I have trained, that itself enough for those observations to understand about the class. But there are few observations, irrespective of my delivery, irrespective of my training, they are not actually understanding, which means I have to give more importance to them. So I'm just increasing the weight of that misclassified samples. So for that, the formula is that initial sample weight into amount of say, right? The previous sample weight into e to the power of amount of say. So sample, this is the formula for incorrectly classified sample. So 1/8 is nothing but my initial sample weight into e to the power of minus 0.7. E to the power of 0.7 is nothing but 0.33, right? So now this is the weight. Now this is the weight for my, incorrectly classified sample. So for incorrectly classified sample, previous weight is 1/8. Right. So now after applying this formula, 1/8 and e to the power of minus e to the power of 0.97, my weight has become 0.33. So 0.33 is more than 1/8, right? Yes or no? 0.33 is more than 1/8. So obviously I'm just increasing the weight of that misclassified sample. Whereas for all the other sample, which is correctly classified, for all the sample which is actually correctly classified, I'm just giving the weight of e to the power of minus amount of c. Sample weight into e to the power of minus amount of c. So this is the formula for the new updated weight for the correctly classified sample. Whereas sample weight into e to the power of amount of c is the formula for new weight for an incorrectly classified sample. Whereas sample weight into e to the power of minus amount of say is the weight for correctly classified sample. So 1/8 into e to the power of minus 0.7 is nothing but 0.05. So obviously this 0.05 is actually less than 1.8, right? because I don't need to give more focus on some student who understanding everything from my lecture. No, I don't want to spend more time on asking some questions to them. I have to give more focus to this, more focus on the students who are not understanding, who are actually struggling to understanding. So I'm just increasing the weight of incorrectly classified sample, whereas I'm just reducing the weight for the correctly classified sample using this equation.
So one question, sir.
Yes.
Sir, when we got that amount of say is nothing but reliability of weak learner. Here,
Yes.
when it says 0.97, after that directly we are going with next calculation, or from that from 0.97 we are inferring whether it is lower or higher.
No, that we will do at the end. We are going to ensemble all those decision. No, so as of now, 0.97 is the amount of say for this weak learner. So like that, we are going to construct so many weak learner. Then while we consolidate the final result, as I told, you are asking your opinion to different many of your friends, and each and every of your friend is telling their opinion. So at the end, while you are consolidating your friend's opinion, for some friends you will be for some friends' opinion you will be giving more weightage. For some friends' opinion you are giving the less weightage. You know, so in that process we will be making the inferences, or we are going to use this amount of say to make the final decision, right? So once we got different weak learner, then we will be while we are taking that final result, what is weak learner 1 is telling, what is weak learner 2 is telling, what is weak learner 3 is telling. So for weak learner 1 is telling like he is having odd disease, weak learner 3 is also telling he is having odd disease, but weak learner 2 is telling that he is not having odd disease. Only one weak learner is telling that he is not having odd disease. Two weak learners telling he is having odd disease, but still that second weak learner which is telling that he is not having odd disease, whose amount of say is very high compared to that weak learner 1 and 3, then obviously I'm just going to go by the decision of my second weak learner, even though only one weak learner is telling that he is not having odd disease, but the amount of say of that weak learner is very high. So I'm just going by the opinion of the weak learner with the highest amount of say. So we will be seeing that, but as of now I'm just using this amount of say to update the weight, for each and every sample. But later on we are going to use this amount of say to make our final decision also. You got the point?
Yeah, sir.
Yeah. So now the kind of idea that you need to have is, initially for all the weight, for all the observation, I have given the equal weight. Now equal weight, which is nothing but 1 by 8. Can anyone tell what is 1 by 8 exactly in terms of value? 1 divided by 8 is 0.125. So initial weight is 0.125 for all the sample. Now for the misclassified sample, incorrectly classified sample, I'm increasing the weight from 0.125 to 0.33. Whereas for the correctly classified sample, I'm just reducing the weight from 0.125 to 0.05, which means I have to give more focus on incorrectly classified sample, whereas I no need to give more focus on correctly classified sample. So that is what the idea. Everyone clear with this? How the weight has been updated? Yes or no?
Clear, sir.
Yeah. So now you can see this newly updated weight table. So it's not new data set. I have just included that weight in this table. So the same data set, previously the weights are 1 by 8, 1 by 8, 1 by 8, 1 by 8. Now you can see the new weight. Because why only for this sample I have given 0.33? Can anyone tell?
It was incorrectly classified.
Because this person weight is less than 176, but still it's having odd disease. So that is what this one case now. Even though his weight is not greater than 176, still is having the odd disease. So this fellow, so in my data set, this is actually incorrectly classified sample. So for that incorrectly classified sample, the new weight is 0.33. All other are correctly classified sample. For all the things I am just giving 0.05. Right? And the weight should be a normalized one. So the weight should be a normalized one, not normalized weight. What does mean by normalized weight? If you add all those weight, you should get 1. If you add all those weight, you should get 1. So here also 1 by 8, 1 by 8, 1 by 8, we have given. Why we have given like that 1 divided by n? If you just add all those weight, the total weight is actually come as 1. But here, if you add all those things, 0.05, 0.05, 0.05 plus 0.33, then 0.05, so on, you won't get 1. So what I need to do in order to make this as a normalized weight, I'm just dividing each and every element by 0.33. I'm just dividing each and every element by its maximum value 0.33. So 0.05 divided by 0.33, sorry, not 0.33, 0.05 divided by sum of all those weights. Divided by sum of all those weight. What is sum of all those weight? 0.05 into 7 plus 0.33. So 0.68 is the sum of all those weight, right? We just sum it up all those new weight. You will be getting 0.68. So now you have to divide each and every number, each and every value in this new weight by 0.68. So 0.05 divided by 0.68, you will be getting 0.07. You will be getting 0.07. So similarly here 0.05 divided by 0.68 is 0.07. 0.05 divided by 0.68 is 0.07. 0.33 divided by 0.68 is actually 0.485. So I have rounded, I rounded off that. So we are getting 0.49. So this is normalized weight. Everyone understood how I achieved this new weight and how I achieved this normalized weight? Any doubt in this? Clear or not?
Yes, sir.
Fine. So once we got this new weight, and from this new weight, the normalized weight. Now listen, how we need to frame that new data set. So I'm just going to frame randomly, but that random process that I'm going to do is such that more representation will come from misclassified sample. More representation will comes from misclassified sample. Say here, if you closely see here, I have written some kind of moving sum number. So what is this moving sum number? Say the first normalized weight is 0.07, right? So here I have given some range like 0 to 0.07. Then for the second sample, I have given the range from 0.07 to 0.14 because it's a cumulative sum. So here it's a first number, so 0 to 0.07. Then for the second sample also, the normalized weight is 0.07. Previously, it is 0.07. So cumulative sum is from 0.07 to 0.14. Then from 0.14 to 0.14 plus 0.07, which is nothing but 0.21. Then from 0.21 to 0.7, because here 0.21 plus 0.49, it's actually equal to 0.7. So 0.21 to 0.7 for this sample, and for this sample 0.7 to 0.77, then 0.77 to 0.84, 0.84 to 0.91, and 0.91 to 1. Right? So just I have depicted this range for each and every sample. Now, why I have written the range is, say now I'm just going to randomly choose some numbers, say between 0 to 1. That is the reason why I have now come up with the normalized weight, because I want those weight range should be between 0 to 1. Right? So if I choose the random number between 0 to 1, if I choose the random number between 0 to 1, do you think like yes or no?
We lost you for a...
We lost you for a...
30 seconds.
Oh, 30 seconds. Sorry. See, if, did you got this? Why?
We got that the range is divided from 0 to 1. Then
the ranges has been formed for each and every sample using that cumulative sum concept. Now I'm just going to pick some random number between 0 to 1. So if I'm picking some random number between 0 to 1, definitely the chance that that random number to have the value between 0.21 to 0.7 is more, right? Yes or no?
Yes.
Because randomly, if I'm asking everyone, so 50 people are there now in your class, I'm asking you to pick some number between between 0 to 1. So obviously, you may pick, of course, you may pick 0.1, 0.2, 0.3, 0.4, different number you will be picking. But anyway, as the span is more here, 0.21 to 0.7, the chance that many of you to pick the number between 0.2 to 0.7 is more than the other range. In the other range also, there is some numbers you will pick. But obviously, the chance that the random number to be in this interval of 0.21 to 0.7 is more. 0.21 to 0.7 is more, right? So see, these are some random number that I'm picking. Say here you can see, say 0.72, 0.42, 0.83, 0.51, 0.63, 0.92, 0.05, and 0.3. These are the random numbers. Now, just see what is the first random number. The first random number is 0.72. Now, in this range, 0.72 is coming for which observation? With respect to this range, 0.72 will come for which observation? This observation, right? Observation with weight 156. Yes or no?
Yes.
Right. So now for this random number 0.72 in your new data set, this 156 weight observation will come as your first observation. If you go and see,
0.72 also comes in 125, sir.
No, see 125 it starts from 0.77.
Okay.
Right, it is actually 0.77 to 0.84, right? But 0.72, 0.72, 0.77, it comes here. So this particular observation now passed into your second level, right? Which means I'm forming a new data set. In that new data set, the first sample is this one. The first sample is this row. Then what about the second random number? 0.42. For 0.42, which observation will come? 0.42 is in this range, right? 0.21 to 0.7. Yes or no?
Yes.
So this observation with the SCS167S will now come into your new data set. Then similarly for 0.83, this one, 125. No S125 will come. Then again for 0.51, this one, SCS167 will come. Then again for 0.63, SCS167 will come. For 0.92, the last observation will come. Then for 0.05, the first observation will come. And then for 0.3, once again, this 167 observation will come. Now, if I ask you, with respect to this random number, how many samples now comes from the misclassified data? In the new data set, how many times the misclassified observation is repeating?
3 times.
How many times the misclassified data is repeating? 5. 5, really? This for 0.42 is in this range, so it will come. Then 0.51, then 0.63 and 0.3. So I think 4 occasions, right?
Yeah.
Yes or no?
Yeah.
Okay, so at 4 occasions, these are those 4 occasions. So when your random number is 0.42 and 0.51 and 0.63 and 0.3, that misclassified sample itself again is coming. Now this is the new data set that we formed. This is a new data set which we formed, which is same as that of your old data set, that is in terms of size. Because how many random number that I need to choose? The number of random number that you need to choose is equal to the number of observations. So in this 8 observations, I'm having 1, 2, 3, 4, 5, 6, 7, 8. So 8 random numbers I'm just choosing. That 8 random number I'm just choosing between 0 to 1. So obviously the chance that this random number to be in the range of that misclassified sample will be more, because for that misclassified sample only I have given more weightage. So with respect to that weight only I have written this range. So obviously that random number chance to be exist in that misclassified range is high, which means with respect to that random number, if I pick the samples to the next level, that misclassified sample will occur more time in my data set. That is the idea.
So it's a kind of upsampling, right?
Yeah, it is. Yeah, it is kind of. That is like that misclassified sample count we are increasing, right? With the misclassified count we are increasing. That is more representation we are actually giving with respect to that misclassified. Of course, it is kind of upsampling, but it is not a kind of traditional smooth technique or something like that.
Yeah.
But we are actually, of course, we are actually increasing the representation of misclassified samples by the technique that I have just discussed with you. Clear up to this?
Yes, sir.
Now, with respect,
I have a question here, so I can interrupt.
Yes, please.
Can we go to that slide number 2?
This one?
Here, yeah, 1 second. So here, so we have considered the gap to be like 0 to 0.04, and yeah, we have found out with the observation of the misclassified one, the 0.491, like we see there's a lot of gap. So most of our random samples that we've chosen, it is falling under that category. But what if, because here, since we have a higher number, 0.49, the gap is more. So that's the reason the random numbers are falling. So will there be any situation where the random numbers that we are choosing will not fall into that? What if such situation occurs? So will it happen or not?
No, it won't happen, because we have actually calculated this new weight using this concept amount of say, right? So after this, say this amount of say has been derived using this formula. So why they have used this formula? By doing all those researches such that whenever there is a misclassified sample, so we have to give more room for this. With respect to that only, this mathematics has been carried out. Here we are just seeing this as a formula. If you just go through this proof of those formulas, you might understand like why they are actually using 1 minus total error divided by total error, all those things, why they are using ln and all those things. Once you understand the proof for this mathematical equation, then you can confidently tell, okay, definitely if I use this new weight that has been derived using the amount of say, definitely the gap will be more for the misclassified samples, because for the misclassified sample only we are actually increasing the weight. For the correctly classified sample, we are actually reducing the weight. So obviously that running sum for the correctly classified sample will be that gap will be definitely low, because we have deliberately reduced the weight. Whereas for the wrongly classified sample, we are actually increased the weight. So obviously that gap will be more. So definitely it will be retained. This logic will be retained irrespective of whatever the big data set is. This gap will be definitely maintained, because we created the new weight by increasing the value for the wrongly classified sample and reducing the value for the correctly classified sample. So definitely this gap will be more for misclassified sample, and this gap will be less for correctly classified sample.
Okay. So it will always apply like that. Okay.
Yes.
And one more thing is, so here, let's say if the random sample is 0.21, it will fall under the fourth classification only, right? Because fourth one or the third one? Because so here it says 0.14 to 0.21 for the third observation. And for the fourth one, it should be 0.22, right? From 0.22 to 0.7.
Yes. Of course, it is 0.22.
Right? Okay.
Yeah.
Okay. Yeah. Fine. Okay. That's clear. Thank you.
Yeah. Fine. So now this process will continue. So now we have reached the point where we prepared our data for our second week learner. Now you have to frame the second week learner from this new data set. How can you form the second week learner from this new data set? Any idea?
Again, you have to calculate Gini.
Exactly. Again, we have to calculate the Gini for chest pain, blocked artery, patient weight, right? So once you calculate the Gini, and you might know for which feature the Gini is less, that will be your weak learner. Then for that new weak learner, you have to compute what is the total error. Then with respect to that total error, you have to calculate what is the amount of say. Then using that amount of say, you have to update the weight for correctly classified sample and wrongly classified sample using the formula old weight into e to the power of plus amount of say and old weight into e to the power of minus amount of say. So now after doing that, you will be getting some new weight. Now with respect to that new weight, you have to form those running sum, and with respect to that running sum, you can choose some new data set. So this process you can keep on do until your bias error and variance error are actually under control or under with respect to the requirement that you have, right? So this is the process iteratively you have to keep on do until you are getting the satisfied performance from your model. So this is how your AdaBoost classifier works. Now, for example, say I have constructed the 5 decision stems like this, right? So keep on, I'm doing again. So 5 decision stems I'm just constructing, and for each and every decision stump, say this is my amount of say. For first decision stump, the amount of say is 0.97. For the second decision stump, the amount of say is 0.41. For the third decision stump, it is 0.32. For the fourth, it is 0.12. And for the fifth, it is 0.2. And I have one column called hard disease. That is the output. Say that is one test sample. Say that is one test sample. This test sample, I'm just applying into my first weak learner. My first weak learner is telling like it is belongs to yes hard disease. Then the test sample I'm applying into the second decision stump. My second decision stump is telling that it belongs to no hard disease. Third decision stump is telling that it belongs to yes, and fourth is telling that it's no, and fifth is telling it's no. So how many decision stumps are telling no hard disease, and how many decision stumps are telling yes hard disease? 2 are telling yes, and 3 are telling no. So if in case of random forest or bagging, we generally go by the maximum opinion, right? But here we are going by that weighted opinion. So what does mean by weighted opinion? We are going to use this amount of say to make this decision. So what is the total amount of say for the stems, which is actually telling like the person is having heart disease? So 2 decision stems are telling like the person is having heart disease. So decision stump 1 and decision stump 3. So decision stump 1 and decision stump 3 are telling that the person is having heart disease. So the sum of those amount of say of these 2 stems 1 and 3 is 0.97 plus 0.32. So the total sum of amount of say for the decision stumps, which is saying that the person is having heart disease, is 1.29. Whereas there are 3 decision stumps which is saying that the person is not having heart disease. The cumulative sum of those corresponding amount of say is 0.41 plus 0.42 plus 0.2 is 0.73. So the total amount of say of the decision stumps, which is saying that the person is not having heart disease, is 0.73. Right? So out of these 2 amount of say, the amount of say for that yes decision stump is actually more than the no decision stumps. So obviously my final decision about this particular test data is yes, the person is having heart disease. Got the point? Even though there are 3 decision stumps which is saying that the person is not having heart disease, I'm just going to make my final decision like the person is having heart disease, because even though only 2 decision stumps are telling that trustability, the reliability of the 2 decision stump is more, because the amount of say for the 2 decision stump is more compared to sum of all the decision stumps amount of say, which is saying that no heart disease. So my final decision will be like, yes, the person is having heart disease.
So how did we reach this table, the 5? Can you just go back?
See, how can I get this final table? Say now, say this is your first decision tree, right? So now say there is one test sample, say one test sample who's say, let me draw it here. So weight is greater than 176. That is say this is yes or this is no. Say this is no or this is no. I'm not using the count and all. Based upon that probability, I'm just allotting this node for yes or this is for no or this is weak learner 1, right? Then weak learner 2, I'm just doing with respect to chest pain. Say chest pain thing is chest pain Guinea is less, so I'm just choosing chest pain. So chest pain is yes, chest pain is no. So it is actually yes or this is, and say this is no or this is. Say the third weak learner is say blocked artery. If blocked artery is yes, say there is yes or this is, and blocked artery is no, say there is no or this is. Say that this is 3 weak learners that I have constructed, right? So now there is one test data for this fellow. The weight, chest pain, and blocked artery. Say the weight is 180, chest pain is no, and blocked artery is also no, right? So by applying this data into this 3 weak learner, what is your decisions? Can you tell? With respect to this first weak learner, for this person is having odd disease or not? Weak learner 1 decision. What is the weak learner 1 decision for?
Yes.
Yes, right? Because greater than 176 means yes or this is. So this path. Let me move this somewhere here. Yeah. So this is the path. Now with respect to this second weak learner is using only chest pain. Chest pain is no. So second weak learner decision is no. What about the third weak learner? Third weak learner is also saying this line. So weak learner 3 is also no. Right now I have to see what is the amount of say. So out of this 3 weak learner, 2 weak learner are saying no odd disease, 1 weak learner is saying odd disease. But I can't go by the maximum opinion here in AdaBoost. I have to see what is the amount of say. Say the amount of say here is 0.9, and amount of say for this weak learner is 0.2, and amount of say for this weak learner is 0.3. Then even though this 2 weak learners are telling that it is no, the sum of those amount of say is only 0.5. Whereas even though only 1 weak learner is telling that it is yes, but the sum of that weak learner which is saying yes is more than the sum of the weak learner which is saying no. So I'm just going to make my final decision like yes, he is having odd disease.
Okay.
Right?
Yes.
So this is how AdaBoost is actually doing the classification task.
Sir, one doubt here.
Yes.
When we are selecting Gini for a weak learner, won't the Gini remain same for all weak learner? Like how will the Gini value changes?
Gini value definitely will change, no, because we are actually framing that new data set for that is we are actually we are not using the same data set for each and every level, right? If you see this workout, initially this is our data. Initially this is our data set, right? Yes or no?
Yes.
Then after forming the first weak learner, we have computed this amount of say new sample weight, all those things, and this is after doing this some random number concept and all those things. This is my new data set, right?
Yes, sir. Only the weights have been changed, but the
no.
yes or no.
No. That whole say now there are so many values which is actually represent so many rows which is having the value as SS167, 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 right here.
Yes, sir. Yes.
So previously there is only one sample to represent this SS167 sample. Now there are 4 samples which is representing it. Some of the samples are not at all there. right? So obviously for this newly formed data set, if I compute the Gini, then I may get the different Gini value for each and every column of data, right? I won't expect that same Gini value that I got before. Are you agreeing that?
Yes, sir. I can see the data change here, but I don't know on what basis the data got changed here.
What basis the data got changed here? Because my idea is I want to give more focus on the misclassified sample. So I'm just doing some process here such that the misclassified sample is appearing more time in my new data. So for this is my misclassified sample. So if you see the new weight, I using that amount of, say I have computed the new weight, I have computed the new weight such that now this one sample alone is getting the weight as 0.33, whereas all other samples are getting the weight as 0.05. Why? Why?
Because only one misclassified data is there.
Yeah, only one misclassified data. So now for that misclassified data, the weight is high. For all the all the other data, the weight is
low.
Using that weight only, I'm just forming this normalized weight and I'm framing this range. So obviously this range is actually more for this misclassified sample, right?
Yes,
0.21 to 0.7. So while I'm doing some random, while I'm choosing some random number between 0 to 1, obviously the chance that this misclassified sample to exist in my resultant data will be more. Yes or no?
Yes,
because
sir.
randomly you are picking some number between 0 to 1. Obviously that chance that number that you are randomly pick is between 0.2 to 0.7 will be more.
Okay.
Right? So obviously whenever say this is a random number, so obviously you can see 0.4 to 0.51, 0.63 and 0.34 numbers are in that range. So whenever a random number in this range of 0.2 to 0.7, obviously I'm just picking that particular row. I'm just picking that particular row, which is actually misclassified samples. So that is the reason why in my new data, the misclassified samples are occurred more time. As it is actually occurred more time, the data nature, the data characteristics has been changed. So as the data characteristics has been changed, if I compute the Gini value for each and every column once again, I will be getting different Gini value. So based upon that new Gini value that I'm getting, I have to choose my root node for my second week learner.
Okay, sir. Thank you. Got it.
Yeah. Yeah. Fine.
I have again a small doubt here in second slide. So when we go to this total error, right? So when we are computing amount to say in the second slide, little top. Can you go little top? Yeah. So here total error for this weak learner is we came when we got the value as 1/8. Let us say here the in the left branch the incorrect one, let's say it is 1. So in that case and the correct one would be 2 and incorrect is 1. Okay, so the total error would be 1/8 plus 1/8 or 1/8 into 1/8. I think you mentioned this, but I forgot. Can you repeat?
2 into 1/8. That is 1/8 plus 1/8 only. That is 2 times.
Yeah, 1 plus, right? Yeah. 1/8 plus 1/8. Okay.
Yes.
Okay.
That you can also write this 2 times of 1/8. So the total number of incorrect sample is 2, irrespective of whether the incorrect sample is exist under left node or right node. Totally, how many number of incorrect samples? Say if there are 4 samples are incorrectly classified, then 4 into 1/8.
Yeah, correct. And so in general question, I mean, this I missed it in the last session. So for the continuous variables, we come across this decision, right? Like weight is greater than 176. So you had said that we have done this in the previous class, like using some moving average, etc. So just wanted to know which session was it? I'll just go through the recording, but just want to know which session was it done? Decision tree, right? Okay. I'll check it. Sir.
So at the end of the decision tree session, I have just told that, and some of you actually asked me to refresh that concept in the next session also. So at the end of the decision tree session, and also in the very next session, I think in which we have started our random forest or the cane, I'm not sure. So that time also I have just briefed you, and also I have sent one document, one Word file like DT. So in that I have just worked out that calculation also.
Okay. I'll check that. So it is in Olympus, no? It should be in Olympus. So
yes, it should be. It is in Olympus also.
Sure. Okay. Yeah. Thank you.
So this is how AdaBoost is actually doing the classification task. Now with this, I'm just moving into gradient descent. So as I told, gradient descent is having some other variants also. I'm just going to focus on the gradient descent mathematics in detail. All other versions of that gradient descent are kind of optimization thing that people did in order to do that gradient descent mathematics in a fast way and a more accurate way, right? So our focus will be on understanding the gradient descent as we understand the AdaBoost now, right? So to say gradient boosting, so you hope you remember whenever while we do random forest and decision tree, I have also quickly briefed you like how the random forest works for regression and how the random forest works for classification. Similarly, decision tree also while we are discussing, we have discussed how the decision tree works for regression and how the decision tree works for classification. Hope we discussed that. Yes or no? Because exactly I don't remember.
Which you are telling, sir?
That is a decision tree, that that concept, everything we have discussed with respect to classification, no. But at the end, I also briefed you quickly how this decision tree regressor works. No?
I think no.
Okay. Anyway, let me.
It will be fine if we revise also.
Yeah.
Sir, quickly, can we go for break if you don't mind? And if other folks are okay.
Now it is 9:30. Okay. Okay, we can have a short break. So how long? I can do one thing. So I can quickly refresh this how decision tree doing the task of regressor. Then we can go for a break, and after break we start a gradient descent. Is it fine?
Sure, sir.
Yeah. See, so in decision tree, actually we made the initial decision with respect to some Gini or entropy or information gain, right? Say if this is a feature 1, if you are doing some split with respect to this feature 1 and you are getting some samples here and some samples here, right? Say you are getting, say here there are totally 500 samples. Then after splitting with respect to this feature 1, say you are getting 300 samples here and say 200 samples here. Is it my voice is breaking?
No, sir.
No, sir.
Karthik, it might be something in your side. Please check it out. Yeah. So 300 samples on this side and 200 samples is on this side. So now the thing is, say if it is a regression task. Say this is a regression task, you are predicting the price of the house, something like that. Then obviously out of this 300, how many belongs to cancer, how many belongs to non-cancer? That is the concept of homogeneous about this node itself, it's not there, right? Yes or no? Out of this 300 sample, 290 samples are belongs to cancer and only 10 samples are belongs to non-cancer. Then I can tell that this is actually more, this node is actually more of a cancerous node. And out of this 200 sample, 190 are belongs to non-cancerous, only 10 are belongs to cancerous. Then I can make the decision like this node is belongs to kind of non-cancerous node. But if it's a regression problem, I'm predicting the house price, then obviously I don't have any kind of how can I tell like this is homogeneous or heterogeneous. So what I have to do with respect to the regression task is, say for this 300 samples, I have house price, right? Yes or no?
Mm-hmm.
For the 300 samples, which is coming under this node after I'm doing some kind of split with respect to feature 1. For the 300 sample, I have house price. Say this regression problem is to predict the house price. Now I'm just finding the mean of 300 house price. Similarly here for this node, I'm just finding the mean of 200 house prices, right? So mean of this 200 house price and the mean of this 300 house price, I'm just calculating. Now I'm just computing the MSC for this node, and also I'm just computing this MSC of this node with respect to this mean. So actual minus mean value, the whole square, of course, summation divided by n, where n1 is the count of this. Here, summation actual minus this corresponding mean value, the whole divided by n2. n2 is nothing but the 200 here in this case. Here n1 is nothing but 300, right? So the idea is, after splitting with respect to some feature, 300 observations are coming here and 200 observations are going there. With respect to this 300 observations, what is the mean price for each and every house will have its own price. So what is the mean price, mean house price? I'm just calculating that. Then how each and every house price, means out of, for this 300 sample, each and every sample will have some house price. How this house price is deviated from the mean value of this particular node, that I'm just modeling as MSC, right? So similarly, this MSC I'm just calculating with respect to this node also. Now I'm just seeing that for this F1, what is the total MSC? For this F1, what is the total MSC? Total MSC is the weighted sum of this MSC and this MSC. Right side node MSC and left side node MSC is nothing but weighted sum. So MSC 1 plus MSC 2, right? So of course, this is the weighted sum. Weighted sum of MSC 1 plus MSC 2 is nothing but the total MSC for this F1. So like this, I have to compute this total MSC for the other feature, F2, F3, F4, F5. So if you have 10 features in your model, for all the 10 features, you have to find the MSC, and which feature MSC is less, that feature you have to use as your root node. There is no concept of Gini or entropy in case of decision tree regressor. So it is just simple mean square error. So for each and every node, you have to compute what is mean square error. Error is nothing but deviation between your actual value and predicted value, something like that we generally tell, no? But here that that MSC we are calculating as the deviation or difference between the actual value minus mean value of that particular node. So 300 observations are coming here. Each and every observation have some house price. The average value of all those house prices are nothing but the mean value of house price under this node. And then each and every value, how it is deviated from its mean, that I'm just modeling as MSC. The same modeling of MSC I'm just doing for this node also. Then I'm just adding these two MSC. Weighted sum of these two MSC is nothing but the total MSC for with respect to this feature. Similarly, I'm just computing the MSC for all the features. Which feature MSC is less, that feature will be my root node. Got the point? Guys?
Yes, sir.
Right? So don't say in case of decision tree regressor, there is no concept of Gini. As this is a SLC residency, that is SLC, so supervised learning classification, we are giving more importance to classification task, right? But this decision tree random forest, all those things we can also use for regression task. So in regression task, the decision tree will be constructed in this way. So only this is the different, and also at the end there is one difference. So once you construct the tree, let me write here. So once you constructed the tree, fine. So say if you have one decision tree like this. So each and every node, you are making the decision with respect to MSC. At each and every node, you are making the decision with respect to MSC. And say this is your final decision. And say this is a final decision tree. These are all the root node. So these are the leaf node. Here leaf node 1, 2, 3, 4, 5, 6, 7, 8. So there are totally 8 leaf nodes, right? So now say for example, one test sample, say in this leaf node, say there are 30 samples, and say in this leaf node, say there are 20 samples. Say in this leaf node there are 15 samples. Say in this leaf node there are 10 samples. Say 5 sample, 6 sample, or say 8 sample. Say 10 sample. Say 20 samples. Right. So these are all the number of samples in this leaf nodes. Right. So totally 8 number of leaf nodes. Say for one test sample. Say there is one test sample, and the test sample is traveling in this direction, and it is reaching here. This is the test input. The test input is actually traveling in this direction. It is reaching this node. Say this is a regression task, right? So now what will be my decision? How can I make the decision about that house price? For the given input, my model reached this node. My model reached this leaf. Now how can I make this decision? Totally, how many number of samples are there in this 8th leaf node? How many number of samples are there in this 8th leaf node? 20 samples, right? Right. So 20 samples are there. So this 20 samples are having the 20 house prices, right? This is with respect to trained data. There are 20 data actually coming in this sample. So this 20 data is having its corresponding house price. The average of this 20 house prices are nothing but the house price value for this test sample. The average of this 20 house price is nothing but the final house price prediction value for this test sample. Are you getting my point?
Sir, we're not considering the outlier in the sample.
Really no need. So of course, but anyway, the sklearn package, I don't think it's actually considering any outlier and all. So it is actually taking that. But anyway, for regression task, always that is one reason people will tell that you have to treat the outlier to the extent that you can by doing the capping and other thing. Because regressions always doing this kind of average computation, or even that linear regression, that fitted line will be sensitive with respect to the outlier. So it is always healthy to treat the outlier while you are doing this kind of regression or task. But say the thing is, even though your data is having outlier, in decision tree, what happened in the sense that outlier based data will go into some other leaf. You can't expect this leaf to have some data which is in normal range, and you have some data which is there in the outlier range. If there is an outlier, what happened in the sense, those outliers will go into some separate leaf, So if your test data is also in the outlier range, then your flow will take you to that particular leaf where the outlier data are there. So that is one advantage of the decision tree. So you no need to, that is the reason why we told, like, for decision tree, we no need to do outlier treatment. But provided that if you are using the max depth value as very less, then obviously it won't grow like that. There is one node for all those outliers. So in that kind of scenarios, when you are having the max depth value as very less, then in that kind of scenario, treating the outlier will give you some kind of benefit. But decision tree as applied, it doesn't have sensitive to outlier, because even if outlier is there, then that outliers will go into some separate leaf. So only if a test sample is in this outlier range, it will travel in that path and it will reach that node. Otherwise, it will travel in some other path and it will reach the node and leaf node. And if you just take the average of all those values in that leaf node, you will be getting that output, which is actually much close to that test sample. Got the point?
Yeah, got it.
Right. So 2 points you have to remember with respect to regression process of decision tree. So the same concept only in the random forest also, because random forest also basically have only decision trees. Even boosting is also have internally some decision tree. How the decision tree works with respect to regressor, if you know that concept, that is enough to explain your random forest regressor or decision tree regressor or any other regressor, right? So 2 things: how it is actually making that root node, how it is computing that first node, and after constructing the decision tree, how it is making that final decision for the test sample. So these 2 concepts you need to know to explain the tree with respect to regression problem. Any doubt? Fine, if there is no doubt, we can take a 10 minutes break at this point. So once you come back, we will start to discussing gradient descent. Sorry, not gradient descent, gradient boosting.
What is the outcome of this decision tree, sir?
Decision tree regressor?
Yeah.
The outcome is, say, I want to say this is my decision tree, final decision tree, right? So this is the test sample. The test sample is like the number of bedroom, area, say car parking facility, something like that. Car parking facility, something like that as an input. Now with respect to this input, I need to apply this decision tree, which is already trained decision tree with respect to the trained data. Now this is the test input. I'm just applying this test input on this decision tree, so that if number of bedroom is 5, say this first decision I'm just making with respect to number of bedroom is greater than 3. If it is greater than 3, it will travel in this direction. If it is less than 3, it will travel in this direction. Like that, I have already constructed my decision tree. So with respect to that new test data, it will travel in one path and it will reach any one leaf node. In that leaf node, I have to see totally how many number of samples are there. So in this leaf node, with respect to the trained data, there are 20 samples are there. There are 20 samples are there. So each and every 20 sample will have its own house price. Now, as I reach this node, I have to take the average of this 20 house prices. Then the average of the 20 house prices, only the house price value for this test data. That is the outcome. Are you getting my point?
Yeah, got it, sir.
Right. So previously it's a classification. Say out of this 20 sample, how many are hard disease? How many are not having hard disease? Say out of this 20, say 15 are actually having the hard disease and 5 are not having the hard disease. Then my flow reached here. I'm just making the decision like this person is having hard disease. Now this 20 outputs are actually regression output, which means continuous data. So once it reaches here, the 20 for that 20 data, what is the house price I have to see? Average of that 20 sample house price is nothing but the house price for this test sample.
Okay, so what are the other metrics that we consider apart from mean? Because most of the time, sometimes we may not accept mean will be the right choice, right? So what are the other metrics that we might go for?
So here,
yeah, I mean, once you get
see why you are saying that mean is not trustable matrix? Because mean is not trustable metric. It's only because of the outlier, right?
Yeah.
If there is no outlier problem, then obviously you can trust your mean. That is what I told. No, so here only similar samples will come in your leaf node in your decision tree. If the sample deviation is more, then obviously those information will go in some other leaf node. Yes or no? So you can trust your decision tree because only the similar samples will ultimately come in the final node of your decision tree. So mean will work fine. You don't need to actually search for some other metrics. If you want, you can take it, but you don't need to much confuse because mean won't be a powerful metric provided that your data is having an outlier. Here, the characteristics of the data which is there in that leaf node is such that the data deviations are actually less. So ultimately, you can use the mean to represent the overall characteristics of those samples.
Okay, how about percentile? Say, for example, out of 20 samples, say mean is maybe a 3, whatever. I mean, I don't know the value, but assuming the mean is a 3, and some percentile of 90 percentile of data, which is around 4. So what will my decision will be wrong if I take a 90 percentile of data?
Yeah, say we are going with the provided. So when we are going with regression with the hope that your output is continuous, right? So if it is continuous, then obviously it is not like all the up to 90 percentile all the values are 3, only after 90 percentile the value is changing as 4. That can't be a real continuous output, right? Real continuous output is actually continuous. So in that case, obviously your decision tree, after applying those splitting with respect to MSC, only the similar data will be there in the one leaf node. Say out of this 20 data, the ranges for this 20 data will be from, say you are predicting the house price, this 20 data house prices could be like say 3 lakh to 3,50,000. So like that. So because if the data is 5 lakh more 5 lakh to 6 lakh house price will come in some other node. So 7 lakh to 8 lakh house prices will come in some other node. So obviously all those 20 data belongs to something for the sample whose house price is say 3 lakh to 3,50,000. So average of this numbers, which is between 3 lakh to 3,50,000, could be the correct value for this test sample. Even if you take 90 percentile value, that 90 percentile value, it's somewhere close to your mean only, right? Provided that that IQR gap is actually too less, because here only 3 lakh to this 20 samples are going to have the value between 3 lakh to 3,50,000. So whether you are going with mean or you are going with 90 percentile, that actually won't make much difference. At going with mean is actually an optimal thing rather than going with a 90 percentile data. Why I want to go with a 90 percentile data for this 20 sample, provided that this 20 sample values are actually changing from 3 lakh to 3,50,000, then my 90 percentile value could be 3,45,000. But why I need to go with 3,45,000? I'm just representing in an average way. Say out of this 20 sample, the data are between 3 lakhs to 3.5 lakhs. So whatever the input data which is reaching that node, I'm just making that output value as 3,25,000. So that could be a kind of balanced correct value for that particular test input. But if you want, with respect to some domain, if you want to push this to 60 percentile, 75 percentile value as the representation for this node, you can do it. But in sklearn, we don't have any option to do it. sklearn will actually tell the final decision with respect to mean only.
Understood. So I'm thinking we have to. Is there a prerequisite that all the data at the leaf node should be a normal distributed? Because the
no need. So no need. It is not normal distribution, something like that. By as it is actually keep on splitting, it will split such that only that the uniform data, only the data which is close to each other will come in one root node. Because say if the deviation will be more, then obviously that MSC will be high. So with respect to that high MSC, it won't actually put that data in that particular node, right? So only if the data is actually close to each other, then only this decision tree mathematics will actually bring those information in one particular node. If the deviation is more, automatically the data will go and sit in some other leaf. So you won't expect that two highly deviated data to be there in the same leaf. In that case only the problem will come. For that, we don't need to make sure that our data is normally distributed at all. By default, this way of splitting the data based upon that MSC value will actually lead to the node such that in the leaf node only the similar data will exist. If the data is deviated bit, that deviated data will automatically go into the some other node rather than be in one node where the deviation is more. You got the point?
Got it.
Fine.
Yeah, got it.
Yes.
Yes. Sorry, sir. I think I took the time for a break.
Yeah, fine. Yeah, sure. Now I think it's 11:55, right? So we can start at 12:05.
Okay.
Raghu, are you asking that for classification? What is the metric to tell that model is correct significantly? Raghu, are you there? I think he's not there.
Maybe
So,
on break, sir.
Yeah. Fine. Shall we start now? I hope everyone is back.
Yes, sir, we can start.
Yeah. Fine. So the next variant of boosting that we are going to discuss now is gradient boosting, right? So whatever that we have discussed just before a break is actually known as ADA boost. So now we are going to discuss gradient boost. So gradient boost, I'm just going to explain for regressor problem. The same way you can also understand the classification problem. The only thing is the matrix is different. So I will be sharing that mathematical workout of how classification has been carried out with respect to gradient boosting. But anyway, this gradient boost and also extreme gradient boost, everything initially has been generated or worked out with respect to the regression problem only. Later on, they have done some kind of modification in terms of metrics and other things, and they have extended that mathematics of gradient boost regressor towards the gradient boost classification, right? So it is better to first discuss how gradient boosting works with respect to regression. Then you just go through how that gradient boosting works with respect to the classification, because the concept is remain same. The only thing is the metrics is slightly differ. So let me first explain this gradient boost regressor. So as usual, I have taken the toy data set. So height, favorite color, and gender. Based upon that, we are going to predict the weight of the person. So weight is an output column, and height, favorite color, and gender are the input column. As weight is an output column, obviously this is a regression problem, and we are going to discuss now how gradient boosting is actually doing this task of regression. So for this, the basic underlying concept remains same, whether it's ADA boost or gradient boost or any other boost, which means it's going to learn from the mistake. And also it's a sequential model. Why say, can anyone tell, we have discussed ADA boost. How initially while I'm telling the difference between your bagging or random forest to boost, I told one main difference is random forest or bagging are actually not a sequential model. It's actually a parallel model. So each and every decision tree are independent of each other. Whereas I told that boosting is a sequential model. Do you really agree that ADA boost mathematical concept that we have discussed is actually a sequential process?
Yes, sir. Because one step and another step is interrelated.
Interrelated, right? Because we have derived the second data set or second bag of data set using the first weak learner output. So after constructing the first weak learner, we identified like which are all the misclassified sample, which are all the correctly classified sample, and based upon that we have calculated the amount of say, and we have changed the weight of each and every sample. Then with respect to the change of weight only, we have constructed the second data set, or then with respect to that second data set only, we have constructed the second weak learner. So the formation of the second weak learner is based upon the output of your first weak learner. So obviously that is sequential. Whereas in random forest or bagging, that is not the case. We are just randomly picking the subset of the sample from the data, and we are actually building the decision tree individually. We are not actually taken the result of first decision tree to form the second decision tree there in random forest or bagging, but here we have done that. So that is the reason why this is a sequential model. So all the boosting, whether it's ADA boost or gradient boost or any other variants, all the boostings are actually a kind of sequential model. And the advantage of sequential process is it's learned from the previous weak learner. So whatever the things which has been missed by the previous weak learner, now the second weak learner is learning that from it. So we are expecting the boosting to do well because it is actually learning from the mistake. So it's doing some kind of corrective process to just to overcome the mistakes done by the first weak learner, or whatever the samples which is actually wrongly classified, we are actually giving that representation more in the second weak learner. So my second weak learner now will have it's now understanding about that mistake classification in much better way. So that concepts, sequential concepts, learning from the mistake concept, all those things actually is there in gradient boosting also. The only difference is the way it is actually forming those base learner is different. The way that AdaBoost is forming the base learner is through decision stump, right? With max depth equal to 1. As I told, you can also use some max depth equal to 2, but more the max depth, overfitting will be more. So preferably 1 or 2 we will be using. But here, how that base learner is actually getting constructed, that is actually important, right? So that actually makes this gradient boosting different from our AdaBoost. So now we are going to discuss that part. So here, as this is an regression task, the first base model or the first base learner is actually known as mean model. It's actually known as mean model. So what is that mean model? So here there is a weight of 1, 2, 3, 4, 5, 6 observations are there. For that 6 observation, we are having 6 weights. Now the average of 6 weight, I'm just going to consider the output of my first base learner, right? Which means it's like mean model. If you remember, in linear regression also, we have compared the performance of my model with respect to the mean model. So how good my model compared to my mean model, that with respect to that only we have defined SST, SSR, R square, all those things, right? So it is such a kind of thing. So without using any one of the input, I'm just using the average value of my output as my base model output. So the initial model is a mean model. So I'm just taking the average of my weight column. The average of my weight column is 71.2. So that is my mean weight or mean output of my first level of base learner. Then with respect to that first base learner, which is nothing but your mean model, I'm just calculating the residue. Residue is nothing but your error. Residue is nothing but your error. So if you see, so for the same data set, I'm just introducing one another column, which is nothing but residue. Why this residue is 16.8 here? Can anyone tell? How I return the residue as 16.8?
Sir, could you please
Value
scroll
minus mean?
little above?
Sorry?
Could you please scroll little above?
Actual or predicted?
Weight minus weight bar, like mean.
Actual minus predicted.
So the first level of base learner, I told like it's a mean model. So the mean model is producing the output as 71.8, which is nothing but average of all my weights, right? So average of my target column is nothing but the mean mean value of my output column. Now the residue I'm just calculating with respect to this mean weight. So the actual weight is 88, and 88 minus 71.2 is nothing but my 16.8. Similarly, for the second value, that weight is 76, but my model is predicting as 71.2, which means at the initial level, at the entry level, my model is actually predicting 71.2 as an output for all the observation. 71.2 as an output for all the observation. So how this mean value is deviated from each and every actual weight, that is nothing but my residue. Got the point, everyone? Yes or no?
No, sir.
Oh, your voice is breaking. You told yes or no?
No, sir.
So you're not getting... Sorry?
I said no, sir.
So you're not getting this point?
Not very clear.
See, the gradient boosting, it starts with the base model. The base model for the gradient descent regressor is mean model. What is mean by mean model? Without using any input feature, I'm just using the average value of my output. That itself I'm just considering as the output for my model. Say I'm just predicting the how much score that you people will score in the final exam of this ML2. So for that, what I'm doing, what is your previous batch? What is the score of ML score of each and every student in your previous batch? That I'm just taking. So in your previous batch, say there are 40 students, the average score of that 40 students that I'm considering as the model. So the average score of 40 students, that is your seniors, is say 70. I'm just predicting each and every one of you now doing this ML2 in this term will score a score of 70. So that is my mean model, right? That model is a poor model, right? I'm not at all using any of the input characteristics of you. I just taking the average score produced by your seniors, and I'm just using that average score as an predicted value for each and every one of you now here in this classroom. In the sense, that is a kind of poor model. So that is actually mean model. We have already discussed that during our regression course itself. Got that? Now, still you are having confusion?
Got that, sir.
Yeah. So now gradient descent, this gradient regression start with the concept of mean model. Now, with respect to this weight, the mean of weight is 71.2. Now this, with respect to the 71.2, I'm just calculating this error, which is nothing but residual. So the actual value of the first person is 88, but the average value is 71. So the difference is 16.8. Similarly, with respect to the second observation, that deviation is 4.8. Third observation, minus 15.8, to so on. So this is the first step in your gradient boosting regressor. Then once you frame this base mean model, you have to construct your first level of tree. You have to construct your first level tree. So for constructing the first level tree, obviously you have to identify the root node using the same Gini concept. Here there is no concept Gini, using that MSC concept. I told no. With respect to regressor, how to identify the root node, you have to use the MSC concept for each and every feature. For each and every feature, what is a MSC? You have to calculate which feature is actually giving you the least MSC, that you have to consider as the root node. So like that, you have to identify the first root node, which is actually producing the least MSC with respect to this data set. So just like that, I have taken like gender is the first root node, followed by height and color, right? So here in gradient boosting, the logic is like people will choose anything between 4 to 16, or for a large data set 4 to 32 as the leaves, right? So they will allow your tree to grow such that it will have at least 4 leaves to maximum of 32 leaves. So for a very bigger data set with many columns of information, they will go up to even 32, or generally it's around 4 to 16. 4 to 16 for a huge data set, even up to 32 leaves they will go, right? So it means in AdaBoost we have just grown our tree such that the leaves are only 2, which means the maximum depth is only 1. So with only one split, you will be getting only 2 leaves. But here you are allowed to split it further. You are allowed to split it further such that you will be getting leaves anything between 4 to 16 or 4 to 32 for huge data set. So it is actually kind of partially grown tree. It is not completely grown tree. At the same time, it is not actually too short tree also, as we discussed in our AdaBoost. It is actually partially grown tree we are using as an base learner here in gradient boosting, right? So that partially grown tree is what is the nodes should be there in that partially grown tree, that you have to identify using Gini or entropy or MSC based upon whether you have a regression problem on your hand or classification problem on your hand. So now, for example, say I'm just splitting with respect to gender. Say gender is actually having the less MSC compared to all other feature. So I'm just using gender. At the next level, with respect to this right node, so with respect to this left node, say height is having the less MSC, and with respect to this node, say color is having the less MSC, so that we are splitting with respect to height and color followed by gender, right? So once I split this, say if gender equal to female and height is less than 1.6, here in the root node, I have written something called 4.2, minus 14.2 and minus 15.2. And here we have written something like 4.8. What is this number? These numbers are nothing but the residue of the corresponding observation which is coming in this root node. Residue of the corresponding observation which is coming in this root node. Just go and see your data. So just remember this, say here the condition is height is less, gender is female and height is less than 1.6. Can you tell gender equal to female, height is less than 1.6? How many data are there? Gender equal to female and height is less than 1.6. How many data are there? 3 data, right?
1, 2, 3. Yeah.
So female is this one, and this one, 3 females. Out of this 3
2 females, sir, which is less than 2.
You said
1.5, 1.4, that's it.
No. See here, the first thing is gender equal to female. If it is yes, then I'm going to check whether the height is 1.6. So how many females are having the height less than 1.6? That is what we have to check here. Totally how many females? Only 1, 2, 3 females. Out of the 3 females, 1 female height is exactly 1.6, but we have to check for less than 1.6. So 2 females. So here there is 1 female whose height is 1.5, and here there is 1 female, the height is 1.4. So for this 2 female, you can see what is the residual value. The residual value is minus 15.2 and minus 14.2. So that is what I have written here. Minus 14.2 and minus 15.2. Have you got this? So when gender equal to female and height is also 1.6, what are all the observations are there? What is the corresponding residue of it? Similarly, when gender equal to female and if height is not less than 1.6, so we have only one sample like this. Gender is female, but her height is not less than 1.6. It is actually equal to 1.6. So her residue is actually 4.8. So that is what here we have written, 4.8. Got it? What is the information that I have written under this leaf node? Here it is. What is the residue? Because what is the error? Because this is a kind of a regression problem. So we are actually predicting this error. So 14.2 minus 14.2 minus 15.2 and 4.8 here. So similarly, here on this side, when gender is equal to female, when gender is not equal to female, because this is under no, and color is not blue. If color is not blue, here actually this is yes, and this is actually no. Color not blue, yes means what?
But why are we not considering for male height parameter?
Sorry?
Why are we not considering the height parameter when it is male and we are only going for color?
No. The thing is, see, the construction of this tree is purely based upon which feature is having the less MSC. It is like, say, first I have to try for all the combinations. Say in this data set, I'm having height, favorite color, gender, these 3 input features. So what you need to do, you have to compute the MSC. As this is a regression problem, you have to compute the MSC for height, MSC for favorite color, and MSC for gender, and which particular column MSC is less, that you have to identify it as your root node. Now I come to know like gender is having the gender equal to female is having the less MSC compared to all other feature. So that is the reason we are splitting initially with respect to gender equal to female. Then after splitting gender equal to female, some observation will come here and some observation will come here. No, with respect to that new observations which is coming on this left side node and right side node, once again you have to do the Gini. Once again you have to do the MSC calculation. So with respect to that data which is I'm getting under this node, I'm just doing MSE calculation, and with respect to that, I'm just getting like height less than 1.6 is having the less MSE. So I'm just using the height less than 1.6 as a rule here. And with respect to this side data for color not blue, for that I'm just getting the least MSE value. That is the reason why I'm just using that color not blue as an feature here to split it further. So you no need to much worry about it here. Just like that, I have taken this tree, but you have to find the MSE for each and every feature for that subset of the data. Then you have to take the decision which feature MSE is less. That feature you have to use as a root node in that particular level.
Okay.
Got the point?
Yes, sir.
Right. So here I'm getting 16.8. So 16.8 means this one, right? So the color is blue and he is male. So if he is a male, obviously he will travel in this. And color not blue is no. So color not blue is no means the color is blue. So the color blue is actually 16.8. So that is the reason why the 16.8 is coming under this. And whenever the current color is not blue and also they are male, there are two observations. So these two observations residue are 1.8 and 5.8. So now this is your tree. I'm not growing it further, but you are allowed to grow this further. You are allowed to grow this further. Again, you can make a split. So such that the number of leaves should be anything between 4 to 16 generally. Even for a complex data, you can allow to split it further, such that your number of leaves should be anything between 4 to even 32, right? But generally 4 to 16 is kind of okay for a reasonable column row data set. So now I have reached how many leaves here? 4 leaves here. So I have stopped with this itself because the data set size is very too small. For this itself is a kind of overfit model because I have only 6 observations in it, right? So, but anyway, I have stopped this partially grown tree. So previously in AdaBoost, if I split with respect to gender, that's it. Gender equal to female, yes or no, that's it. With respect to that, I'm just making the decision. But here it's a partially grown tree. After splitting with respect to female, I'm just splitting with respect to height, and also I'm splitting with respect to color, and that with respect to that partially grown tree, I'm just going to make the decision now, right? So now this is actually the 1 week learner. It is not a complete week learner as we discussed in our AdaBoost. AdaBoost only is actually using the complete ideal week learner because the max depth equal to 1. Here it's a partially grown tree, but still it is a weak learner. It is not actually completely making the correct decision because you can see some kind of overlapping here. There are 2 numbers, right? But still it is not a kind of completely grown tree. It's a partially grown tree. So the decision of this, it's actually a kind of weak. You can't expect the very bingo prediction from this for a big data set. Here there is only 6 observations. So we may get the very close appropriate result, but for a long data set, just splitting with respect to only female and only height and height and color may not give you the proper correct result. So this is partially grown tree. We are actually constructing as a first level weak learner here in gradient boosting, or second level weak learner here in gradient boosting. The first level weak learner is your mean model, and second level weak learner is your partially grown tree. You are allowed to grow your tree such that it should have the number of leaves anything between 4 to 16. So once you've done this, you have to combine these 2 models. The first model is your mean model. For that the value is 17.2, and the second model is this partially grown model. For this partially grown model, the structure is like this, right? So now I want you to apply this observation 1.6 blue male in this tree. Along with this mean model. Can you first tell me, if you pass this data 1.6 means height is 1.6, color is blue, and gender is male. If you apply this 3 information in this decision tree, what is your residue? What is your output?
16.8.
16.8, right? Because gender equal to female, but here in this observation, the gender is male. So it will travel in this no direction. Then it will check whether color is not blue. Actually here color is blue. So color not blue is actually no. So it will travel in this condition, in this direction, and it will reach this node 16.8, right? So with respect to this data, this partially grown decision tree, it's actually giving the output as 16.8. And mean model output, irrespective of whatever the data that you will give, the mean model output is always 17.2. So the overall output now, it's 16.2 plus 16.8. Sorry, 71.2 plus 16.8. So for this given input, the overall output is 71.2 plus 16.8. So in total, the value is 88. Got the point? Total, the value is 88. Now just go and see what is the actual output for this data. So this is the same data, 1.6 blue male. For that, the actual output is 88. Now I got 88 here through my gradient descent. Sorry, through my gradient regression. I'm just getting like while I'm applying this 1.6 blue male through this mean model followed by partially grown tree, I'm just getting the correct value as 88 for this given input. So basically your gradient boost regressor work in this way only. But as this is a very simple toy data, and also even though I'm telling that it's a partially grown tree, almost this tree is actually becoming a kind of fully grown tree, because only 3 features, and for the 3 features only 6 observation I'm just having in this. So obviously this is actually a kind of fully grown tree. But imagine if you have 10,000 observation, 1 lakh observation, and 20 column of data, 10 column of data. So obviously there will be a lot of misclassifications will be there. So obviously you won't get the correct bingo prediction like this. And also one more thing, here while I'm constructing that partially grown tree, here I'm having 2 values, 2 residues. Here also I'm just having 2 residues. So you can take the average of 2 residue to represent the overall residue of this node, overall error of this node. So 14.2 plus some 15.2, the whole divided by 2 is nothing but this value 14.7. And also the average of these 2 residues, 1.8 and 5.8 is around 3.8. That is the overall representation of residue for this node. So with respect to this partially grown tree and mean model, for this given input, I'm just getting the correct output value as 88, which actually completely match with our trained data, right? Maybe for the new incoming data, the value will be slightly differ. But anyway, this is a kind of clear indicator of overfitting problem. This is happening because I have actually grown this tree to greater extent. Have grown this tree to a greater extent. So I have to cut down this tree. I should not grow this tree to this level, even though only 4 leaves, but 4 leaves is too much with respect to this toy data set that I'm having. For a big data set, 4 leaves is actually produce more error, but here this data set size is very small. The 4 leaves itself is producing a kind of bingo prediction for me. So generally what they will do to avoid this overfitting, they will use the concept called learning factor. So we have already discussed this learning factor in gradient descent, which is actually control the variation in beta naught and beta 1. It will actually control the step size of coefficients in gradient descent. The same kind of learning factor concept we are actually using here to control the convergence. So if you see, this is my base model. Yeah.
Hello.
Yes,
sir. I didn't get why we are qualifying this as overfitting.
Why we are? Yeah. The thing is, say for the given input, I'm just getting that exact output 88, right?
Correct.
So if it is a partially grown tree, tend to have some kind of error, right? So here I don't have any error at all. Okay. Are you getting? Say with respect to only one partial grown tree and mean model, if
it is not blue condition, right? Because we have taken average, that line you will get some deviation, right?
Yeah, of course. If you are stopped your decision tree at this point itself, rather than splitting this color not blue, if you are stopped your thing here itself, obviously you may not get a complete correct output, but still it is actually a kind of close. But anyway, you won't get exactly as 88. So that is the reason why I'm telling that that base learner should be partially grown tree. More you grow, obviously you will be getting the you will be making your model as a kind of overfit model. So you should not grow your tree to greater extent at this level itself. If you grow your tree to greater extent at this level itself, then you can go with a simple decision tree. You don't need to use boosting at all. The boosting works with the concept of learning the mistakes which is made by the previous weak learner. Your first weak learner itself a fully grown model and it is not at all making any mistake. Then what is the point in actually going with the boosting algorithm? Only if we make some mistakes with respect to the first level of the weak learner, then the second level of weak learner will be constructed such that it will taken care of those mistakes carried out by the first level of weak learner. So that is the kind of idea. So here in this data set, why it is actually coming very correctly, because I told like you have to grow your tree such that it should have number of leaves from 4 to 16 or 4 to 32 in for a bigger data set. But so that is the reason why I have grown this tree such that it is having 4 leaves. But 4 leaves itself, it's too much for this data because I have only 6 observation and I have only 3 features. As I am having only 6 observation and 3 features, 4 leaves itself, it's too much. So 4 leaves, even only one data goes into 4 leaves, 4 observations has been classified, right? Only 2 will actually overlap. So it is actually a kind of overfit model only. So almost all the leaves are becoming completely homogeneous. So that is the reason why with respect to this toy data set, it is actually overfitting. But for a bigger data set, this you won't get a kind of correct bingo prediction at this stage itself. So, right?
Okay, sir. Yeah, thank you.
Yeah. So, but anyway, I don't want this convergence to happen very quickly. That is, after building my mean model, I'm just building my model to predict the residues. That is the deviation. If I just my model understand the deviation, this deviation is nothing but error, right? This, what is this? Minus 14.7, 4.8, 3.8, 16.8. This residue is nothing but your model error. Now I'm training my model to learn about the error. I'm training this weak learner, this tree based weak learner objective is to understand the error, to learn about the error. So once it learn about the error, then it can do the prediction well. It understand the error once, error in a clear way. If it able to model that error, if you able to predict the error, then obviously this is the mean model, and this much deviation could have been happened. So if it adds that error with that mean, then obviously that is your correct output, right? Because mean is the average representation and residue is nothing but the deviation from its mean. Once you train your model to capture the deviation, then if your model have the ability to predict the deviation, then the deviation, if it acts with the mean, then it will become your correct output. So that is the idea, learning from the error, learning from the mistake. So here it is actually exactly learning, exactly predicting, but we don't allow this exact prediction. One way is actually cutting down the tree. Of course, we are going to, by default, we are going to do only partially grown tree only. In this case, the partial tree grown tree itself, it's look like a kind of completely grown tree as we have less number of samples. The other way to control this overfitting problem or overfitting nature of your gradient boosting is by giving some learning factor, right? So while I'm training my model to learn about the error, while I'm training my model to learn about the residue, I'm just moving my model in a slow way, right? Just understand some part of the error, just understand some part of the error, just understand some part of the error. Like that sequentially, I'm just letting my model to understand the error or learn the error slowly, right? So for that, I'm just using one learning factor as 0.1, right? So learning factor value can be anything between 0 to 1. Obviously, we can tune while you are doing the grid search CV. With respect to grids gradient boosting, you have one parameter to tune as alpha, that is learning rate. So learning rate, you can use different values and you can evaluate your performance of the model, like for which alpha you are getting the high performance. But anyway, here, if I introduce the learning rate as 0.1, with respect to this learning rate of 0.1, can you tell now for the same data, what is your output? Same data means gender equal to male and color is blue. When gender equal to male and color is blue, with respect to this tree now, what is the value that you will be getting?
It will
Gender
be
sorry?
It will be reduced by factor by 0.1.
Is reduced by factor by 0.1, which means 71.2 plus 0.1 times of 16.8, right?
7288.
Right, because the 16.2 will be multiplied with 0.1, not the 71.2. The 71.2 is there. Now the error, we are not allowing my model to just memorize the error. I want my model to learn about the error slowly and gradually. So we are using one factor here. So
Excuse me, sir.
Yes.
Color is not blue. It comes under 3.8, right?
Yes, but here color is blue.
Okay.
In the sample.
Okay. Got it.
In the sample, the color is blue. So it's flow through this condition no. So here 16.8. This 16.8 will be multiplied with 0.1 in the sense it's become 1.68. So this 1.68 plus 71.2 is now around only 73, right? So 72.9. So now this is the predicted weight: 72.9, 71.7, 69.7, 71.6. So each and every sample, each and every row, if you apply in this tree along with this mean model, and tree will produce this predicted weight for you with a learning factor of 0.1. Right? So now if you calculate the residue with respect to this predicted weight, this is the predicted weight by your mean model and your first grown tree, right? The first level of grown tree combinedly predicting the output as 72.9, but the actual output is 88. So the residue is 15.1. Similarly, for the second observation, the actual weight is 76, and my mean model along with my first level of tree, it's actually predicting the output as 71.7. So the residue is 4.3. So like that, it is actually predicting for all the data. Now this is the new value of residue. This is a new value of residue. Now, once again, you have to construct the second level tree. So once again, you have to construct the second level tree now to predict this new residue. So while you are calculating the MSC, now you are for each and every node, you have to consider this residue as an output. So previously that residue is something else, right? Previously the residue is 16.8, 4.8, minus 15, 1.8, 5.8, minus 14.2. With respect to this residue, because our objective is to capture this error. So this residue is my output column now. Now I want to find which feature is having the less MSC while predicting this residue. So with respect to that, I have constructed this tree. So now the concept is, now after building that first level of tree along with mean model, now I'm getting some new residue. So now once again, I have to find the MSC for this height, MSC for this favorite color, and MSC for this gender with respect to predicting this residue, right? So based on that, you have to construct your newly partially grown tree, second level newly partial grown tree you have to construct with respect to this new residue. Anyway, in this workout, I have using the same tree, right? So for example, the same tree branches I have chosen, but anyway, this tree formation will be happen with respect to which input feature are actually giving the less MSC with respect to newly computed residue, right? So that part a machine will take care of, but anyway, manually if you want to do, you can do by calculating MSC with respect to each and every node, and which feature is actually giving less MSC, that you have to consider as your first root node in your decision tree. So like that, you have to keep on do for the left side, right side things. So here, just like that, I have considered the same tree, but it may not be the same tree. You may get different features at the different node positions for this new residue that we have got. So now with respect to this new residue, for each and every input, this is a tree. And you can see minus 12.7, minus 3.7, the new residue values are coming in leaf, and more than 2 residues there, in the sense we have to take the average. So we have to take the average. So now this is my newly constructed tree. This part is my newly constructed tree. And previously I have constructed one tree, and previously I have my base model. So now this is my complete sequence. Base model plus learning factor into first partially constructed tree plus learning factor into second partially constructed tree or partially grown tree. Right? It's look like both the trees are same, but as I told, with respect to that new residue, whatever the root nodes that you are getting, with respect to that, we have to construct this tree. But anyway, here for just calculation purpose, I have just taken the same tree once again. But you can see the residue values are getting changed here. So now with respect to this new structure, once again, I have to find what is the residue by applying each and every input. So which means the first input where gender equal to female, gender equal to male, and color is blue. So if I apply this 71.2 plus 0.1 into 16.8, similarly plus 0.1 into 15.1, 0.1 into 15.1. Yes or no? If you apply that first sample, gender equal to male and color is blue, what is the result? What is the result? Can anyone tell? What is the error, or what is the residue value, or what is the value? What is the weight value you will be getting for a gender equal to male and color equal to blue with respect to this gradient boost tree structure that we are getting, which is having two partially grown decision tree and one mean model?
.74.
So why? So here I'm just simply writing. What happened? Why it's not changing? So gender, the test input is gender equal to male and color equal to blue. So this will travel in this direction. So here it is 0.1 into 16.8. And once again, it will travel in this direction. And here it is 0.1 into 15.1. So which means initial mean model is 71.2, right? 71.2 plus 0.1 into 16.8 plus 0.1 into 15.1. So which is around 74. Yeah, some of our participants is telling 74.39. Right? So now if you see, after introducing each and every the new partially grown trees from 71.2, now my output is actually moving towards 88, right? Because for this data, 88 is the correct output. 88 is the correct output. Now I'm just gradually, slowly moving from 71.2 to 88, right? Initially it is 71.2, then after that it's just become 72.9. Now it's becoming 74.39 at the end of the second level of partially grown tree. Now with respect to this whole tree structure, if I compute the residue for all the input, if I compute the residue, this is the new residue that I'm getting. 13.6, 3.9, minus 12.4, 1.1, 5.1, and 11.4. So this is the, if you see, I have written only the residues. So this is the first residue that I got. This is the first residue that I got with respect to mean model. This is the residue that I have got with respect to mean model and one level of tree. And this is the output that I got, or the error that I got, or residue that I got with respect to mean model and two weak learner. This is the mean model residue. This is mean model plus weak learner 1 residue, and this is the mean model plus weak learner 1 plus weak learner 2 residue, right? So you can clearly see the residues are actually reducing. Yes or no? So after the introduction of each and every new partially grown tree in our gradient boosting structure, you can see that residuals are actually keep on reducing, right? Yes or no?
Last one is increasing, no?
No, how come? Last one also this is actually minus. You just check it out. It should have supposed to be minus. So for what is the last data? 1.4 blue female. So it's equal to female means it's female and 1.4. So female means it will come in this direction, and 1.4 means it comes here. It's minus 14.7. So I haven't written it wrongly there. Here also it is minus 13.2. So it is minus 14.7 into 0.1 and minus 13.2 into 0.1 plus 71.2. So obviously it could be around minus 11. It's not plus 11. Right?
Yeah.
Right. So it is minus 11. Right. So just change that. So the thing is, after introducing the different partially grown trees sequentially, I'm just reducing the residue. So at one point of time, this residue will become close to 0, or once this residue are good enough for you to present your result to your client, you can stop at this point. You can stop at this point. Otherwise, internally, you can tune this model like with different n estimators, right? So here the n estimator is 2 because two trees only I have constructed, right? So if you give n estimator equal to 10, you can see with respect to n estimator equal to 10, what is your output? With n estimator equal to 20, what is the output? N estimator equal to 30, what is the output? So which n estimator is giving you the best output? You can stop with that. So this is how your gradient boosting works.
So the residuals which are in minus, so that will go below the average, right?
Sorry?
The residuals which are in a negative. So if we add to the average value, so the value will be lesser than the average value.
No, that is why. Yeah, why the residue is coming in negative? Because not average. That is the say we have the actual weight. No, we have actual weight. No. So if your predicted weight is actually more than your actual weight, then in that case you will be getting the residue as negative.
Correct.
Yeah. So we are not actually taking the average and that. So the residue is actually for each and every observation. So 88 minus 72, it's actually 15. Whereas 56 minus 69, it is actually minus 13.7. So ultimately, so whether it's positive or negative, that doesn't matter for us. We have to reduce it, reduce the deviation, whether the deviation on the positive side or whether the deviation is on the negative side. That doesn't matter for me. I want the deviation to be as minimum as possible. So we can clearly see there this deviations are actually keep on reducing. Initially it's 16.8, then it's 15.1, then it is 13.6. So here also for the second sample, third sample, the deviations are keep on increasing. Even in the last sample, it is actually minus 11.4. Here, if you see, I have written minus 11.4 only. Once again, while I'm writing here, I missed that minus sign. So the residues are keep on reducing. So obviously, at one point of time where your residues are in the acceptable range or when your residues are close to 0, then you have to stop this growing process. You have to stop your gradient boost growing. So at that time, say when you are actually having 10 different sequence of trees and you are reaching the residue value under 0.5, then you are stopping there. Then obviously that will be your final model. So one test input coming in the sense that test input you have to apply into those 10 different trees that you have constructed, plus you have to add the mean model output. That is the final predicted output for that particular test data. That is what you have asked? The reason for this negative sign or something else?
No, I got to know. I mean, I got on one more dot when we're checking the negative value, which is say from 16.8 is the residual, and we reduce 20%, like say 0.1, 0.1. So it will be like 13.6. So the thing is, if you keep reducing, if you increase the learning factor like 0.1, like say it will be like 0.5, which is 50% of 16.8. It is around 8. So as you said, when are we supposed to stop it?
So say when we are supposed to stop it, say this is each and every sample error, right? So here at the this is the value that I got after at the end for the n estimator equal to 2. Yes or no?
Yeah.
This is 13.6, 3.9 minus 12.4, 1.1, 5.1, 11.4 is the output that we got for n estimator equal to 2. Why I'm calling that? Because 2 trees only is there, so n estimator equal to 2. Number of trees is nothing but your n estimator. So now with respect to that, you can compute MS0.
Yeah.
That is, you can just take the square of each and every number and take the average of those, so that you will be getting that MSC, right? Then you just if that MSC is fine for you, you can stop it. Otherwise, you just grow your tree with one more level and see what is your MSC. See what is your MSC. See what is your MSC. Just explore your model for different n estimators, and for which n estimator you are getting the least error, that will be your final model. So how that MSC will be calculated? This is the error for each and every observation. Sum of and average of all those errors is nothing but your MSC. So which n estimator is actually giving you the least MSC, that you can consider as your final model.
Least MSC is basically, if you keep increasing the learning factor to 1, then it will be like overfitted, and the errors will be definitely lesser. Then
yeah, but that's why. So that is why by keeping the learning factor low, by increasing the number of trees, obviously you can move towards the correct output, right?
Yeah. But so we intentionally reduce. I mean, we intentionally put the learning factor from the beginning of saying 0.1, and we start increasing the learning factor and increase to that 1, then we'll meet the overfitting, which is the actual value. So we are, I mean, as you said, we are supposed to stop at the lower error. The lower error basically, if you pick it 0.99, then 0.1, I mean 0.01 is a lower error. So how can we say that? I mean, when are we supposed to stop it?
So your question is like, if you are actually using some high value of alpha, this convergence may happen very quickly. That is what your question, right?
No, sir. I mean, the number of estimators is fine. I was asking as per the lower value, lower error. That is the one we that is the case that we are supposed to stop it.
Yes.
But here we intentionally started from the beginning, which is a lower factor of 0.1, and keep increasing it out. Assuming if we have 10 estimators and it will reach to the 1 learning factor, then we meet the actual value.
No, it is not like learning factor we are reaching 1. So what do you mean by learning factor we are reaching 1? So it is like say learning factor is actually always 0.1 only. So we are actually gradually moving towards your actual output by keeping some constant learning factor. We are not actually increasing the learning factor for all the trees. The learning factor is actually only 0.1, 0.1, 0.1, 0.1 only. Or if you are keeping 0.2 for all the trees, it's going to be 0.2, 0.2, 0.2 only. So what happens if I choose the high learning factor, my model may tend to quickly fit with respect to the trained data, but for the new test data, it may not. It may produce some more errors. So that is the reason why you have to see combinedly both the bias error as well as the variance error. So for this alpha equal to 0.1, so what is your bias error that you are getting? That is actually this residue. Once you make your residue as close to 0, then that's fine. So you are stopping it and you are actually using that model. And also for that model, you have to apply some new test data. For the new test data, what is the error that you are getting? What is the performance that you are getting? So if that performance deviation is more during the training stage, for the trained data, you are getting some error. For the test data, you are getting more error. Then that is a problem of overfitting. So once you understand there is a problem overfitting, then which means you have to come back and once again you have to grow this tree, or you have to play with this alpha, and you have to reduce this alpha, or you have to reduce the max depth rather than growing this tree to 8 leaf, you have to just grow your tree only for 4 leaf, and so that at what point you are actually getting the less bias error, and also you are getting the less variance error, that you have to choose as your final model.
Okay, so the lower the error, which is the residuals, which is close to the 0, we have to stop. But the number of estimators, say for example, the estimators are given 10, and the residual still not 0, which it might be still close to the 0. That point we should take a decision saying that, okay, we should suppose we were supposed to stop the estimators, or we have to increase the number of estimators.
So say the thing is,
right?
say you are allowed to keep on increase the number of estimators, but if you are keep on increase the number of estimators, definitely at one point of time you will be getting the error something close to 0. But the thing is, your model will become overfit because you are keep on increasing in the sense definitely it will close to that 0. But what happened in the sense when new data comes in the sense, the new data may not follow the same pattern. So obviously with respect to that new data, you will be getting more error. It is like overfitting your model. So that is the reason that N estimator you have to use in your grid search CV. For each and every N estimator, what is your bias error and what is your variance error? Obviously by increasing the N estimator, you may reduce the bias error, right? But whether reducing in bias error will also at least keeping your variance error constant or reducing your variance error too, that we have to check it out. If on the name of reducing the bias error, if your variance error is increased in the sense, your model is not trustable. So that is the kind of thing you have to check here. Exactly, I have written this point only. The residue are reducing slowly at each level. With the trade-off between bias and variance, we can stop this algo. So you should not focus only on bias error. Bias error means reducing this train stage residue to 0. You also keep on check what is your variance error, and you should not allow your variance error to shoot, right? So you have to come up with the proper trade-off for what estimator I'm just getting the reasonable bias error without increasing the variance error. That should be your final N estimator. That you can get it through your grid search CV. No, we already discussed how to apply the grid search CV to find the correct value for N estimator and all those things. Using that, you can just explore your model for different different combination of N estimator, and you have to see for which N estimator you are getting the bias error and variance error to be in control, so that you can consider as your final N estimator for your model.
Okay, basically the bias and variance should be in the balanced state. In that case, stop it.
Yes.
Okay.
Right, but hope you people remember how to check that using grid search CV. Basically, grid search CV will give you the best parameter only with respect to bias error. But I have taught you how to see that result table of CV2. That is a CV results like with grid search CV. How to see that detailed table. In that table, you have something called mean score and also standard deviation score. If you want to make the decision with respect to variance error, you have to use that standard deviation score. So like that cross-val score with the variance error we have discussed, and also grid search CV with the standard error and mean error I have demonstrated to you people. So you have to apply all those concepts to make the decision about which N estimator is actually giving less bias error without increasing the variance error more. That N estimator you have to choose as your final model estimators. So this is about gradient boost regressor, right? So say all other variants like XGBoost and LGBM, light gradient boost. So in XGBoost, that X stands for extreme. So extreme gradient boosting. So in extreme gradient boosting also the kind of same concept, right? So people used to find the similarity score and gain and the same almost the same concept only, but the only thing is the way that they are constructing the decision tree, it's slightly different. So in gradient boost, in extreme gradient boosting, one another advantage is they are actually smartly using the pruning also. there is one another hyperparameter there in extreme gradient boosting as gamma. Using that gamma value, they are actually checking whether the model is actually overfitting or not. Here, there is no other, no such an option in typical gradient boosting. We have to just keep on grow, and we have to just apply grid search CV or cross-val score to understand our bias error and variance error. Based upon that, we have to make the decision like whether my model is overfitting or not, and which is the parameter, which is the N estimator that I can stop so that my model is not overfitting. Whereas in extreme gradient boost, the regularization parameter is also there, part of that algo. So using that gamma value and lambda value, we can actually control the overfitting during the model building process itself, right? And also light gradient boosting is there. Light gradient boosting in terms of performance capability, how quickly it is doing without using much of your memory. So they have just optimized that same gradient descent algorithm, and they have named as light gradient boost. And also there is one another variance of gradient boosting is available, which is nothing but categorical gradient boosting. In categorical gradient boosting, there is CAT boost algorithm. You no need to do even encoding, right? So that CAT boost algorithm have the ability to encode the categorical variable by its own. You have to just tell what are all the columns which are categorical variable. So just give that data into your model in the sense with that information, like in column 2, column 4, column 7, column 8, there are categorical information. It will just apply the appropriate encoding by itself, and it will give you the model result. So like that, there are different variants, but all those different variants of gradient boost will actually work in the same principle. First, it starts with the mean model, then it will just build the first partially grown tree, and the first partial grown tree rate will be controlled by your learning factor. So the first partial grown tree objective is to predict the deviation, to predict the error produced by your mean model. So always your mean model will produce the error. If you have the ability to predict that error produced by the mean model, you can easily compute what is the output for the given input. So how to predict that deviation, or how to predict the residue produced by the mean model? For that only we are constructing the partially grown tree. So while I'm predicting that, I'm not letting that prediction to be happen just like that. So I'm just moving in a proper direction gradually. So we are controlling that process through learning factor. So so by constructing the first level of partially grown tree, I'm just trying to capture the deviation produced by my mean model. But that capturing is not enough. I can't completely capture all the deviation. So I'm just building one another partially grown tree in a sequence. Now this second partial tree will try to learn the residue produced by the previous tree. So previous tree error is nothing but the residue. Now that residue has been predicted by the second level of tree. Now the second level of tree will produce some residue. That residue or that error now will be used to train the third level tree. Now the third level tree will now learn the error produced by the previous tree. So like that, I have to keep on including different partially grown trees until my model is learned properly about the residues. So this is how your gradient boosting works. Any doubt in this?
So are we going to learn classification also in this, or?
Classification, I will be sharing the thing like this. I have made one workout and I have clearly given the comment and formulas. So now I will take you to this Jupyter notebook in implementing all those things. And also we have to discuss stacking, right? So stacking and voting we will be discussing in the remaining time. So I have in a detailed way, I have explained the same thing with respect to the classification also. So I will be sharing this PDF file to you people, so you people can just go through it. The only thing is that here it's a mean model. No, here the initial model is mean model in your regressor. Here that initial model is the logit model. So we have to calculate the probability, and from that probability we have to calculate the logit, and using that logit as a base model, what is the error? That error we need to predict by the partially grown tree in the consecutive stages. Only some formulas and other things will change, but anyway the flow is same. This is the first model is a base model. The base model, the error in regression is a mean model. Here it is a logit model. That logit model or mean model is the poor model. It will produce lot of error. Then we are going to keep on construct the different trees at the next level to predict the error made by the previous model. So that process is same. The only thing is the metrics are different. There the metrics is residue and mean model. Here the base model is logit model, and the metrics is probability and logit ratio. So that is the only difference. Apart from that, the flow is same. I will be sharing this and you people can go through this.
Okay.
Right.
Sir, can we also cover this this one, Bayesian search optimization for hyperparameter tuning?
No, it is not there in our content. We have only grid search. We are not having the Bayesian optimization in our syllabus itself.
Okay.
Yeah. Right. So this is about these two boosting technique, ADA boost and gradient boost, and also other boosting techniques are the slight variants of this. I have I will be sharing that classification. How I have explained the ADA boost with respect to classification, and I have explained the gradient boost with respect to regression. I will be sharing that same mathematical workout for classification problem with respect to the gradient descent. You people just go through it. Now I will be moving to voting and stacking classifier. I will be moving to voting and stacking classifier. So these also an ensemble techniques. So voting classifier and stacking classifiers is also an ensembling techniques. But how this ensembling technique is differ from the previous ensembling techniques like bagging, random forest, and boosting? In the sense, if you see whether in bagging or random forest or in boosting, the base learners are homogeneous. Yes or no? The base learners are homogeneous in all our previous ensembling algorithms. What I mean by base learner is homogeneous?
Same learner we are using.
Same learners. Like in decision tree, all the learners are actually decision tree. In bagging, of course, decision tree is preferable, but in logistic regression, KNN also you can use. But if you use KNN, all the base learner must be KNN. Right? It is not like one base learner is KNN, one base learner is logistic regression, something like that. So all the base learners should from the same family. So even here in ADA boost and gradient descent, all the base learners, apart from that mean model, you can't really call it some machine learning based learner. Apart from that, all the learners are actually kind of decision tree based learners only. So in all the ensembling techniques that we have discussed, the base learners are homogeneous in nature. Whereas in voting and stacking classifier, the base learners can be heterogeneous. Which means for a given data set, I can use logistic regression, I can use decision tree, I can use random forest, I can use gradient boosting, I can use different machine learning algorithms, and I can ensemble the result produced by different machine learning algorithms to make my final decision. I can consolidate the results made by different machine learning algorithm to find my final decision. So that is nothing but this voting classifier is all about. So let me write this. Say I just build the logistic regression. decision tree, random forest, say naive Bayes, say KNN, and say some gradient boosting, right? So for one given data set, I'm just constructing all those 1, 2, 3, 4, 5, 6 models. Say logistic regression is telling that it belongs to class 1. Decision tree is telling that it belongs to class 2. RF is telling that it belongs to class 3. Naive Bayes, it's telling that it belongs to, sorry, just make 2. RF is telling that it belongs to C2. Naive Bayes say it's telling that it belongs to C1. KNN and Gaussian gradient boosting saying that it belongs to class 2. So out of this 1, 2, 3, 4, 5, 6 models, 1, 2, 3, 4 models are telling that it belongs to class 2, and only 2 models are telling that it belongs to class 1. So the hard voting method will go by this. There is 2 method of voting. One is hard voting, the another one is soft voting. The hard voting method will just count like how many models are telling that it belongs to class 1 and how many models are telling that it belongs to class 2. So here in this case, 4 models are telling that this test observation is belongs to class 2 and 2 models are telling that it belongs to class 1. So the final decision is like this test data is belongs to class 2. So this is how your hard voting will work. But soft voting will work in slightly different way. That is one another voting strategy, which is known as soft voting. How that soft voting works? In soft voting, it will calculate the probability. It will calculate the probability. What is the probability that it belongs to class 1? Right? Say this model is telling that all are class 1 probability. All are class 1 probability. Or say whether it's class 1 or class 2, even now. Say here, say I'm just writing its corresponding probability value. So say here the probability value is 0.6. Here the probability value is say 0.65. Here the probability value is say 0.8. Say here the probability value is say 0.7. Here the probability value is say 0.8. Here the probability value is say 0.9. Right? So now there are 4 classes which are telling that it belongs to class 2. Now what is the corresponding probability? The probabilities are 0.65, 0.8, 0.8, 0.9. So it will take that average probability. It will take that average of those probabilities. So 1, 2, 3, 4. Similarly for C1, it is 0.6 and 0.7, the whole divided by 2. Right? So what is the average class 1 probability and what is the average class 2 probability? Which one is high? If C1 probability is greater than C2 probability, then it will make the decision like it is belongs to class 1. If C2 probability is greater than C1 probability, then it will make the decision like it belongs to class 2. This is how your soft voting works. This process is known as soft voting, right? So voting is a simple process. There is no extra mathematics and all it's getting involved with the voting. There is no new algorithms and all it's related to voting. Voting is the ensemble of heterogeneous model. Voting is the process through which we are ensembling the decisions of heterogeneous model. Whereas in bagging, random forest and boosting, we have actually assembled the decisions of homogeneous model. But voting and stacking are heterogeneous model ensembling approach. So in voting, we are actually ensembling the results produced by different machine learning models. So if I just take the count information alone, like how many models are telling that it belongs to class 1 and how many models are telling that it belongs to class 2, based upon the max vote, if I go with the decision, then it is on hard voting. Rather than going with that count, if I go with like what is the probability for each and every class, right? So if 4 models are telling like it belongs to class 1, what is an average probability? With what confidence it is telling that it belongs to class 1? and with what confidence it is telling that it belongs to class 2. So if class 1 probability is actually greater than class 2 probability, then obviously I'm just making the decision like it belongs to class 1. If class 2 probability is greater than class 1 probability, then I'm just going to make the decision like it belongs to class 2. So that is how your voting classifier works. So there is no extra mathematics or extra algorithms. It is just like ensembling the different heterogeneous models.
There is no constraints, right, sir? When to use hard voting and soft voting?
There is no rules, but the thing is, we have to just see like say sometime what happened in the sense after I will apply different model on my data set. Some model will be good in terms of bias error. Some model will be good in terms of variance error. Then if I want to achieve one common model which actually good in terms of both variance error and as well as the bias error, I will be using the voting classifier to with the models which is producing the good output in terms of bias error, and also the model which is producing the good output in terms of variance error. Then I will be constructing the voting classifier using that. But whether soft will give you the better result or a hard will give you the better result, that actually by applying it only we have to see. There is no constraint, but generally soft method, it's actually more preferable than the odd method. So sometimes your model is telling that it belongs to class 1, but if you see the probability, that probability value is 0.6, then with 60% confidence it's telling that it belongs to class 1. So so what happened? Still there is a kind of 40% evidence that it belongs to class 2, right? So even though that predictive class is correct, it is not actually telling that with more confidence. So if you want to bring that part also, then you can go with the soft voting, because soft voting results are more trustable than the hard voting results, because soft voting results are taken by the probability. So a model which is actually predicting the class 1 with 0.6 and another model is predicting the same class 1 with a probability of 0.9, your soft voting will give more importance to that model which is actually predicting with the probability of 0.9. So in that case, always if you are making some decision with respect to how good that probability value, how high that probability value, that kind of models are more reliable. So in that case, soft voting could be preferable, but we can't have any kind of proof or a mathematical evidence to tell that always the soft voting will give you the better result than hard voting. We have to apply both and we have to see. I have shared one script with you people. In that I have demonstrated all those things. Implementation is simple, just one-liner code. So once you just implement your model through hard voting and soft voting, see the result in terms of bias error and variance error, and then you can take a call whether you have to go with hard voting or soft voting for that given task or for that given problem.
Sir, do you have any weightage method also?
Sorry?
Weightage kind of algorithms?
Latest?
Weightage.
See that by default that stacking algorithm in the voting algorithm in sklearn, I don't think it is supporting weighting. It supports weightage because this probability itself, it's a weightage, right? This probability itself, it's a weightage, right? Say if one model is actually producing the probability as 0.8, whereas another model is producing the probability value as 0.65, which means this 0.8 model is having more weightage than the 0.65. So while we are taking the average, that weight factor is actually getting incorporated, right? Yes or no? So if say suppose say you have a C1 that is for C2, you have all the probability like this 0.55, 0.6 plus 0.55. You are taking the average. Whereas in C1, only two models are telling like it belongs to C1, but the two model probability are 0.8 and 0.9. Definitely this probability value is higher than this, right? Yes or no?
Yeah.
right? So obviously, even though only hard with respect to hard voting, it will tell it's C2, but with respect to soft voting now, it is actually telling C1. Because so obviously it is actually what with respect to weight of this probability, right?
But this weight will vary by observation. So
weight will vary by
observation,
not observations.
So
it
if
is
I have a new entry, then the probability will be something else.
divided by 3.
Yeah, I mean, it can be anything. What I'm saying is like, if I'm just saying whatever is the decision of random forest, I'll just take the 30% of the decision. And KNN, I'll take 20%. So overall, it will be 100%, something like this.
So if you want to do anything like, say, like for random forest, I have to give more importance, whereas for KNN, I have to give less importance. You have to do that manually only, externally. So once you got this probability values, or once you got the class decisions, then you have to manually do that externally. Your stacking and other thing, your voting won't do that. Your voting classifier won't give different weightages for different model. So it doesn't have that kind of knowledge like random forest always do the prediction well. So give more weightage for random forest, but give less weightage for naive. That kind of idea I don't have. If you want, if you feel like that, externally we can do that.
Okay. Yeah.
Yeah. So this is about voting. Then the next ensembling technique is stacking. Say stacking and voting, don't think like I'm just hurrying up, because there is no separate math and other things to discuss with the stacking and voting classifier. This is just ensembling different model outputs. That's it. There is no separate algorithm or separate mathematics is getting involved with stacking and voting. As for voting, there is two methods: hard voting and soft voting. I have told how to how that hard voting works and how the soft voting works. Similarly, stacking is an heterogeneous ensembling. It's an heterogeneous one. So multiple model output we are going to stack, or we are going to ensemble to get one final output. But here the things is that way that we are making that one single output, it's slightly tricky or slightly different. So in what way? In the sense, let us explain that. Let us see, let us take, I have 10,000 sample and 10 features, right? So 10,000 sample and 10 features. Now I'm just splitting this into, say, some 80-30. 8,000 into 10 and 2,000 into 10, right? So I'm just taking 8,000 samples separately and 2,000 samples separately. Let us explain why I have split it like this and what is when I'm going to use this 2,000. Now with this 8,000 samples only, I'm just going to build my different models. So of course, in order to build this different models, once again, I may split this into 70-30, like 5,000 sample for training and say 6,000 data for training and 2,000 data for testing. That is 70-30 split, 70%, 30%, right? Whatever the number that you are getting. Testing, and just using this and using this train model, using this train portion of the data, I'm just building so many models. And I'm just building so many models like logistic regression, random forest, KNN, say AdaBoost and gradient boost, right? So 5 different models I have constructed using this train data, and I'm just using this test data to tune this parameter, right? This is a train data, and this is the test data. So I'm just applying this test data on this model, and I'm checking whether the model is overfitting or not. If it is overfitting, I'm just tuning my model, right? So I'm just tuning my model for the best parameter and other things by using this train and test. I'm just making sure my model is perfect. My model is perfect in predicting this 8,000 data. in this 8,000 data, I'm just using 6,000 data for training, and I'm building my model, and I'm just tuning this model, and I'm checking the reliability of my model using this test set, and I'm making sure that my model is actually doing well. Each and every model, it's actually producing its own high performance. So with respect to logistic regression, what is the maximum performance I can extract from logistic regression? What is the maximum performance I can extract from this random forest? What is the maximum performance I can extract from this KNN and this AdaBoost and gradient boost? All those things I'm just doing with respect to this 8,000 data, right? So once I have finalized my models, once I have tuned my final model, now I'm just calculating the probability. I'm just calculating the probability for this 5 models by applying this 2,000 data. By applying this 2,000 data. So the thing is, now LR, RF, KNN, AB, GB. So these are all my different machine learning model that I have constructed with respect to this 8,000 data. Now on this model, I'm just applying this 2,000 data, right? So after applying this 2,000 data on my logistic regression model, it will give me what is the probability of class 1, right? Say it's a binary class problem. It's give me some probability like for the first sample, the probability is 0.2. For the second sample, the probability is 0.5. The third sample, the probability is 0.8. So on, the probability is 0.75. So this is for first sample, second sample, third sample, so on, 2,000 samples. Right? So similarly, my RF will give the probability. Once I apply this 2,000 sample into this RF model, it will give its probability. The probability is 0.15, the probability is 0.7, the probability is 0.9, so on, the probability is 0.8. Right? For the 2,000 samples, what is the probability with respect to RF? Similarly, with respect to KNN. And this is with respect to AdaBoost. This is with respect to gradient boost. This is with respect to gradient boost. So now this is I'm forming one data set itself using this probability value. The column title are what is the LR model probability for this 2,000 observation? What is the RF model probability for this 2,000 observation? What is the KNN model probability for this 2,000 observation? And also what is AdaBoost and gradient boost probability for this 2,000 observation? Now, for this 2,000 observation, I also have the output, right? Yes or no? Because the whole data is actually 10,000 cross 10, which means 10,000 observation and 10 column of data, and say that in the 10 column of data, one column is the target, right? Which is nothing but your output. So for this 2,000 data also, I'm just having the output. So output is, say this is class 1, this is class 1, or say this is class 2, this is class 1, this is class 1, so on, and this is class 1, right? So now using the probability value of the model that I have trained using this 8,000 data, I'm just framing, or I'm just forming one new data set itself. I'm now framing one new data set itself, right? So previously in voting classifier, once I got the probability for each and every model, then I'm just taking the average of those probability, and based upon that, I'm just making the decision. But here I'm just arranging all those probability value for those 2,000 observation, and I'm forming one new data set. Where the input columns are probability for different machine learning model, and the output column is what is the actual output for that particular test observation, or that particular observation that I have not used to train my model previously. Now I'm just using one new machine learning algorithm. To to predict this output. To predict this output using this inputs. Right? For this algorithm, the inputs are your LR, RF, KNN, AB, GB probability values, and your output are your actual output, whether it belongs to class 1 or class 2. So now this itself actually becoming one data set, and I'm just using one machine learning model to predict this class with respect to this probability. With respect to this probability. So this is how your stacking algorithm works. So in voting algorithm, just for each and every test input, what is the output provided by your LR model? What is the output produced by your RF model? What is the output produced by your KNN? What is the output produced by your ADABUS? What is the output produced by your GB? Just take the average of it or just count it and just produce the output for that one test observation. Here, I'm just using some part of the data separately, like this 2000 data I have kept it separately. And now I'm just building one machine learning model itself to predict the probability produced by your previous stage classifiers. You people got this point? It's a little bit tricky, but it is like I'm just finding the probability using the first level classifier. Then I'm just using one another machine learning model itself to predict the output using the probability values produced by your first level machine learning classifier. That is the idea of your stacking classifier. So this is the second level classifier, or people will call this as a meta classifier. Meta classifier or second level classifier, which actually use the probability value produced by your first level classifier as an input. Then with that input, it actually builds the machine learning model to predict the actual output for this separate section of the data, which I have not used for this model building. That is base model building. Are you getting this point? How stacking classifier works? Algorithms are not different. The mathematics and all not different. How logistic regression works, how RF works, how KNN works, how ADABoost works, how gradient boost works, that and all remains same. The only thing is, after applying all those algorithms, each and every algorithm will give some probability value for this portion of the data. I'm just using those probability value as an input, and I'm just building one separate machine learning algorithm. I'm constructing one separate machine learning algorithm to predict the class from its probability values.
So, but how will we decide which algorithm we'll use for stacking?
Which algorithm means whether LR, RF, KNN, AB, GB.
Yes.
Yeah, you can use all the algorithm. So just like that, you can use all the possible algorithm and you can stack it. You can stack it. So whichever the algorithm will confidently tell that it belongs to class 1, that effect only will be used. Again, you can use here this ML model is actually a kind of random forest model, or again you can use the gradient boost, or again you can use any other machine learning model to predict this C1, C2 using those probability numbers. So you can even use all the machine learning model possible, and with that you can build your new machine learning model to predict the class based upon the probability value produced by each and every machine learning model. Otherwise, rather than using all, you can also smartly use say, after analyzing each and every model individually, if you feel like random forest is doing well in terms of bias error, but variance error is a little bit high, whereas a gradient boost model and ADABoost models are doing well in terms of variance error, but bias error is a little bit high, then in order to bring one common model, you can combine the models which is actually producing the best in terms of bias error, and also you can use the model which is producing the best in terms of variance error, so that if you stack all those models, you will be ended up with one common model which is doing well in terms of both bias as well as variance.
So, sir, here we can do overfitting based on the meta model, right? Meta classifier, what you told.
Overfitting.
Yeah, in case of overfitting, we can do, that kind of regularization on the meta classifier, right?
No, stacking classifier won't generally overfits. because stacking classifier, it's actually ensembling the probability decision of each and every model. The overfitting nature of your stacking classifier generally is less.
Okay.
When your model will overfit, so if you are just asking only one opinion, you are actually traveling in only one vision that you are having. With respect to that only you are actually making the decision, then there may be a chance that it will overfit. Now we are asking the opinion from different models. You are asking LR model, you are asking RF, you are asking KNN, you are asking AdaBoost, you are asking gradient boost. Then also you are not just taking the average of all those probability, or you are not going by the count information of those model output. You are actually once again building the machine learning model. Now this meta classifier is actually learning this probability pattern, for each and every observation for different machine learning algorithm. Based upon that, it is actually predicting if probability for LR is 0.2, if probability for RF is around 0.15, if the probability for KNN is 0.2, if the probability values for AdaBoost is around 0.4, and probability value of gradient boost is 0.1, then it may belongs to class 2. So this pattern, it is actually learning. This learning you can do with respect to logistic regression or decision tree or gradient boost or some other machine learning algorithm. Whatever the machine learning algorithm you want, you can use as an meta classifier. So which means rather than making some kind of odd decision by seeing this probability value, or even if it's a soft decision in case of soft voting by simply averaging it, I'm just using one another machine learning model itself to predict the class from this probability. So that is how your stacking will actually works.
Sir, I can see in SQLM they have given final estimator or number of estimators. So how we are performing the performance of the model on training data, like rest of the 8,000 data?
Can you repeat your question once again?
Okay, so I'm saying we are building this probability data on 2,000 records.
Yes.
So the final algorithm, whatever we'll use, that will produce some accuracy and other performance it will produce, right?
Yes.
What about 8,000 records? Are we not taking the performance of those?
No, see this using this 8,000 records only, each and every model that we have tuned, each and every model we have constructed. Right. So this for training each and every model or building each and every model, I'm just using this 8,000 data. Once I have finalized this model, the best LR, best RF, best KNN, best AB, best GB, doing all those hyperparameter tuning and other thing, I'm just using that best models to predict this output for this 2,000 data. Then with respect to this 2,000 data, only I'm just doing this meta classifier. So this, say if one test input comes, for example, say you want to you have one 10 test input. For this you have this 9 features, or say 9 features, because as I mentioned here, 10, one is for target column, right? So you have 10 features, 9 features, F1, F2, F3, so on, F9, right? So now what happened, this with F1, F2, F3, so on up to F9, your LR model will be get constructed, your RF model will get constructed, your KNN and AB and GB, for all the model that you have trained, this 9 features will get applied, right? So each and every model will produce the probability value for this test input. Say here the probability is 0.2, here the probability is 0.4. Here after applying your test data in this KNN, you are getting the probability as 0.7. This is giving 0.8 and gradient boost is giving 0.7. Then this become the test data. Even though initial test data is F1, F2, F3, so on, F9. Now your test data is actually 0.2, 0.4, 0.7, 0.8, 0.7. Now this test data will get applied into this meta classifier. Now this meta classifier will accept this probability as an test input, and it will produce the output as whether it belongs to class 1 or class 2.
So this sampling technique is happening, dividing in 8,000, 2,000 internally, right?
Yeah, internally. We don't have any control.
Okay.
Actually, it's working same like out of bag error, like we are handling random forest, right?
Yeah, of course. It is like out of bag error that say, but anyway, it is not like
Not
this.
like similar, but same way.
Yeah, of course. We are actually applying this 2000 data that we have not used for this 8000, and we are actually evaluating how good my model in predicting this 2000 data that I have not used for building this individual model. But I'm not testing this 2000 data on each and every model individually in LR. What is the ability of LR to predicting this 2000 data? What is the ability of RF to predicting this 2000 data? I'm not checking that. If I check like that, then it is exactly like that out of bag. Now what I'm doing, I'm just using all those model and I'm applying this 2000 data and I'm producing this probability. With those probability, I'm just building one another machine learning model to predict the class using the probability values produced by your previous stage machine learning models.
So in this case, let's suppose I'm trying to predict on training data only. So if you see that sometimes we try to predict on training and test both. So for example, test data I have separately, and I'm just trying to predict on training data. So this 2000 records will work internally as a training, and rest of the 1000 records will work as a test data, right? Internally.
Yeah, of course. Say internally, it may, but we don't have kind of a clear thing. But maybe this 2000 data, once again, it need to evaluate its performance, right? So for that internally, it may even split it. But this is the overall idea, right? So this is like, so this, even though I have told so many things in sklearn, we are going to write this in one single line, right? So, but the thing is, this is actually hiding some part of the data to build your first level classifier. Then that hidden data has been applied on those first level classifier to predict the probability. Using this probability, it is actually constructing the meta classifier to predict the classes. That is the overall flow.
Yeah.
Sir, that split 70-30 is random, right? Or always 70-30?
No, actually here for explanation, I have given this 70-30 and all, but in sklearn, because my the thing is you have to hide some data. You should not use all the data to build your model, because once you use all the data to build your individual models, then there is no point in actually applying the same data once again and finding this probability. For that purpose, I have done like this. But anyway, in sklearn, internally it will do with cross validation. So all the possible combination, it will actually use for training and it will use for testing. So like that, it will actually perform internally in sklearn, right? But the idea is you have to use some portion of the data to build your individual model, and you have to use some other portion of the data to just find the probability by applying those data on that individual model. Then you have to use one another machine learning model to predict the class from that probability. So the one underlying point is you should not use the same data that you used for your classifier stage 1 for your classifier stage 2 also. If you use the same data, then there is no point in it. So obviously your model will do well. So you have to deliberately hide some data. Then you have to use the data to build the second level meta classifier data set. So if you use the whole data, 10,000 data for here also, then out of the 10,000 data, 2,000 data for which once again you are finding the probability, then there is no point in it, because already you have just leaked the data to your model. Your model will learn the pattern well. So obviously it will do this prediction well for this 2000 data also. That is the reason why I have deliberately hidden it. But in stacking classifier internally, using cross validation, they are actually splitting the data and they are actually doing this process for all the possible portion of the data. So you no need to worry about whether I have to split it to 70-30 or 80-20, all those things, because internally while doing it in a cross validated way. All the possible combination it is using for training and it is using for testing. So you can trust your stacked model results in sklearn very well. Right?
Sure, sir, and share this board picture, sir. Hope you're saving it.
Yeah.
Thanks, sir.
Yeah. right? So this is about voting and stacking. There is no extra mathematics getting involved in it. So it is about how we are going to ensemble the output produced by different base models, right? So I have shared this Jupyter notebook with you, right? Because as we actually line by line executed all those concepts, I don't think that you people have any problem in understanding this coding part. Anyway, I think we have already worked on this planned data set, right? So this is kind of a multi-class problem. So for which I have applied all those bagging classifier, voting classifier and stacking classifier, all those things I have applied on this data set also. Let us see here. These are all the things that we have already discussed. Implementation of AdaBoost and XGBoost and all very simple, straightforward. Just import the AdaBoost classifier and say in AdaBoost classifier, I'm just passing one argument as the base estimator. In base estimator, what is base estimator? It's a decision tree with a max depth one, right? Because we have discussed that. AdaBoost, your decision tree with the max depth one is your weak learner. So decision tree classifier max depth one I have defined as a weak learner. Then in AdaBoost classifier, I'm just making this base estimator which is equal to weak learner. And I'm just giving n estimator equal to 10. And of course, you can also use grid search CV to tune this n estimator. So that's it. Once I have done this cross-val score and I'm just applying my input and output, I'm just calculating what is the mean error and what is the bias error and what is the variance error. So similarly, XGBoost classifier also the same thing, right? Just XGBoost classifier of you have to put your input and output, nothing else, right? Of course, different parameters you can tune. You know how to check all those parameters. You can see that help section of XGBoost, whatever the parameters which is there, like all those decision tree hyperparameters also you can tune with respect to XGBoost, because XGBoost is also having the decision tree only as an base learner. So how many leaves that you want, we discussed, 4 to 32 is the kind of leaves generally we want. So max leaves you can just explore for different values from 4 to 32, and you can see for which leaf your model is actually producing the better performance. So I just let the grid search CV part, because already we done the grid search CV for some other models like random forest, Kane and all those things. The same concept only the parameters is going to change. The way that you are going to apply the grid search CV and understanding the variance error, bias error, all those things remain same, right? So here what I have done is, say I have constructed the 5 different models. So CLF1, CLF2, CLF3, CLF4 and CLF5. So CLF1 is logistic regression, CLF2 is KNN, CLF3 is random forest and Gaussian and XGB, right? Then I'm just using the voting classifier. So from sklearn.ensemble, import voting classifier. So this is how you have to define your estimator. So estimator you have to define as a list. Within that list, each and every element is one tuple. So in that tuple, the first element is the name of that particular learner. So here the first model is a logistic regression. So I'm just giving some name, some string, right? So LR, comma, logistic regression, and comma in another tuple, k nearest neighbor. For that, the name that I'm giving is KNN. Then the third one is random forest classifier. So that is, I'm just defining the name of that random forest classifier as RF, and Gaussian NAV, NB, and XGB classifier, XP. So whatever that you are giving as a name for your model, that could be anything. So here I have given LRNN. If you want, you can give any name. But the second element in the tuple is your function name. So your function name. So once I define the estimator list, simply you have to call this voting classifier. Voting classifier of estimator is equal to estimator. What is there in my estimator? In my estimator, logistic regression, k nearest neighbor, neighbors, random forest, and XGB classifier is there. So internally, all those models will be get executed on the given data set, and voting method I'm just defining. If I give voting equal to hard, so that result will be produced using the hard voting method. If you give soft, it will use the probability value, and that average of probability values will be used to make the final decision. So implementation of the voting classifier is as simple as this, right? So similarly, I'm also seeing individual results, right? So now I have my all those classifiers like CLF1, CLF2, CLF3, CLF4, CLF5, and also I have my voting classifier vote 1 and vote 2. Now I'm just applying everything in a smart way, right? I just one single for loop, I'm just running all those algorithms by zipping those classifier model name, comma, that user defined name for each and every model. I'm just using the cross-val score, and I'm just running this for different I. What is I? In I, that CLF1, CLF2, CLF3, CLF4, CLF5, vote 1, vote 2 will come. So for each and every algorithm, in CLF1, it's a logistic regression. For logistic regression, what is the bias score and what is the standard deviation? Then when I equal to CLF2, then it is, I think, a random forest. It's KNN. For KNN, what is a bias score and what is the a variance score? Now I'm just simply printing all those things. Now this can use to compare your model performance, right? Even in your examination, they may ask you to compare different model performance, in the sense, no need to separately execute each and every model, right? So smartly you can use a for loop like this, so that you can execute all the model performance in one single go, right? So this is the LR model, this is KNN model, this is RF. So XG is doing well, and hard voting and soft voting, of course, soft voting is slightly doing well compared to hard voting here. But compared to individual models, RF and XG, your hard voting or soft voting is not actually really doing great, right? So RF is 0.77 and XG boost is 0.78 we are getting, and also the variance error, you can see 3%, not percentage. Here I have used only standard. If you want percentage, you have to divide the standard deviation by its mean, so that it's become coefficient of variance, right? So do all those modification by yourself. So, and also implementation of stacking classifier is also very simple and straightforward. See, the same way as we define the estimator, you have to define the estimator for stacking classifier also. This is the first level classifier. So logistic regression, random forest, naive Bayes, and XGBoost classifier I have defined here. Now what I have done here, stacking classifier of estimator is equal to estimator. This is first level classifier. Then the final estimator. What is this final estimator? This is meta classifier. After implementing, so we have written, no, after implementing all those different individual models, this is actually first level classifier. I have to compute this probability value, and with respect to that probability value, I have to build one new machine learning model. That new machine learning model, it's actually meta classifier. Here that meta classifier or final estimator is random forest classifier. So logistic regression, random forest, and Gaussian naive Bayes and XGB will produce 4 different probability values for each class. That probability values that I'm training with respect to this random forest classifier, right? So internally, that splitting and all will take care by your stacking classifier. Stacking classifier will actually do internally using cross validation. It is actually using all the portions of the data for training and testing. Here, while I'm explaining on board, I have just splitted the data into 70-30, something like that. I have explained, because if I explain this with cross-val score and all, it will much confuse. You don't need to much worry about that splitting. That splitting process will take care by your sklearn internally by cross-val score, right? So different portion of the data actually used for both training and testing, and it makes sure that your model is actually building, predicting some probability value for some portion of the data, and for some other portion of the data, it is actually for some portion of the data, initially all the models are formed. Then for some other portion of the data, the probability values has been calculated and the final model has been built and its performance has been evaluated. So just in one single line, you can implement this stacking classifier, right? So stacking classifier for this data set, it's not actually doing well. Actually, if you see, the variance is actually getting increased with respect to stacking classifier. But anyway, this data set that I have used, it's a kind of handmade data set. I have told, no, this plant CSV data set that I have constructed for only less amount of data, right? If you see, only around 120 rows are there. So splitting that 120 rows into different sections with respect to the stacking classifier is not really reliable, right? So we need some kind of huge data to make the model to learn properly. So that is the reason why stacking classifier is not really doing with respect to this data set, because this is having only 120 rows. But anyway, for some high complex data set, you may see that stacking classifier will actually do the job much better than the other individual classifiers. So this is about the implementation part of the stacking classifier and voting classifier. So as for concept of voting and stacking, there is no extra mathematical equation, something like that. It is like arranging the base model results in a proper direction to get the proper results. So in that way only, stacking and voting classifiers we need to learn. Stacking and voting classifier really don't have any kind of extra mathematics in terms of its process. Only the sequence that we need to know in what way it is actually aggregating the different model results.
Sir, one doubt.
Yeah.
What is the key similarities or difference between the GB and extreme gradient boosting?
So I told no. So it is say extreme gradient boosting is actually using some other techniques, like it is actually using two other parameters like lambda and gamma. So the role of this lambda and gamma is actually making sure your model is not actually overfitting, right? So in gradient boosting, in a typical gradient boosting, we don't have that option. We don't have that option of checking while constructing the tree. We are not actually much worried about the overfitting. The only constraint or only thing that we are actually making is choose the number of leaves of each and every partial grown tree such that it should be there between 4 to 32, something like that. We are not really worried about whether that partially tree that we are constructing is actually really overfitting or not, right? So of course we are giving the alpha value as 0.1 or something, but we are not actually really checking whether this is overfitting or not in gradient boosting. But here in extreme gradient boosting, there are some parameters through which they are also doing the process of pruning. They are also doing the process of pruning. If the after growing that partial after growing that tree, that at the each weak learner level, we are actually growing some tree, no? So once we have that partially grown tree, they are checking like whether the tree is overfitting or not using the parameter called lambda and C. If it overfits, they are actually pruning it. They are actually pruning it, which means they are actually cutting the last level, right? So that they are actually making sure your model is not actually really overfitting. So that is the reason even here in this example, we can see like your XGBoost are actually giving the less variance. You can see here that XGBoost variance is 0.03 compared to all other models, where XGBoost variance error is actually less. And also it is giving the better performance in terms of bias. But say that is the kind of a tricky thing, right? So in machine learning world, if you try to increase the bias error, if you try to reduce the bias error, your variance error will increase because bias variance stayed off. So if you try to reduce the variance error, you may overfit your model. So as a result of you overfitting your model, your variance error will increase. So bringing both the things less is actually a little bit tricky. But gradient boost is doing that. That extreme gradient boost is really doing that, because during each and every stage of the construction in extreme gradient boosting, they are also checking the overfitting nature, and appropriately they are actually pruning the tree level. But here in typical gradient boosting, we are not doing that. We are actually just using that say max depth equal to 4 or maximum leaf equal to 8 we are giving. With respect to that 8 only, that each and every level the decision trees will be getting constructed. Whether that 8 leaf decision tree is overfitting or not, we are not actually really seeing during the construction of the gradient boost. Once we completely finish the gradient boost, we can go and we can change the max leaf for different numbers, and we can do some kind of exploration. But in extreme gradient boosting, during internally in the algorithm building step itself, this process will be taken care of. That is one greater advantage of your extreme gradient boosting. And also it is an optimized algorithm in terms of memory allocation, or in terms of execution speed and all those things. Extreme gradient boosting is actually doing well compared to your typical gradient boosting catch optimization, your local mission catch optimization. For that and all, some extra libraries, extra things which is there, which actually use your hardware resources of your system effectively to implement it. That is one part. But in terms of machine learning part, it has the ability of handling the overfitting nature by its own through the model building process itself. That is one extra advantage that extreme gradient boost is having. You got the point?
Sure, sir. Thank you.
Yeah. So I hope that everyone received the script. You please go through the script. In terms of implementation point of view, you won't have any challenge, because these are all we have discussed. This multi-class thing I think we have discussed in our previous session. So only how to apply the stacking classifier, voting classifier, I have demonstrated in the script. So you please go through it, and if you have any doubts, you can ping us. Any other queries?
So this PDF files, right, which you had explained today, I couldn't find that in Olympus. Can you also upload that?
Yeah, I will upload that. I am not shared that with people yet. So just now itself, I'm just sharing all those 3 PDF. One is for AdaBoost, and 2 is for your gradient boost. One for classification and one for regression. I will be sharing that.
Yeah, thank you.
Yeah, thank you.
So what are the other classifiers also, sir, apart from the voting and stacking?
Other classifier in boosting family, there are 2 more classifiers. One is LGB, light gradient boosting. So because gradient boosting is sometimes a little bit heavy in terms of computation, because as we are doing, say, alpha value, if you are choosing 0.1, slowly it will actually move towards your correct output, right? So computationally it is a little bit heavy. In order to overcome these kind of stuffs, LGB has been used. LGB stands for light gradient boosting. Right. So as I told, it's a kind of shortcut way of doing the same mathematics. So internally, something they have done smartly, so that the same thing you can achieve with respect to in an optimized way by utilizing less memory and in quick time. So in that way, LGB is actually better thing. And one more model recently many are using is CAD Boost. So CAD Boost is one another model. Recently only people outsourced that, right? So previously one Russian company used it to have this model, and they claiming that they are getting the better result with respect to that. Recently they have outsourced that, and that one that CAD Boost model used to give lot of reports by its own, right? But tracing the mathematics of that CAD Boost model is very complex. So you can't find even proper documentation, and that help section doesn't have much of information about how exactly it's doing those stuffs. But the advantage of that CAD Boost model is you no need to do the encoding, right? So if you have some categorical data, you can keep that categorical data as it is in your data set, and you can feed that data with categorical column into your CAD Boost model. Your CAD Boost model have the ability to handle those categorical data by its own by applying appropriate encoding techniques.
Okay.
So these 2 are the other 2 models. Apart from that, of course, ANN is there. Artificial neural network is there. That we are not having that in our syllabus, and also SVM is there. So support vector mission and artificial neural network. These are all the other 2 powerful algorithms, especially if you deep learning and all. It's I think maybe while you are studying your deep learning, you might study your neural network, because for any deep learning algorithm, neural network is a fundamental element. That neural network we can also use as an basic ML algorithm to do the prediction with respect to structured data. But neural network can be effectively used to do the prediction for unstructured data like images, text, signals, and all those things. So SVM and neural network are the other very popular machine learning algorithms.
Okay.
But if you see how SVM works, SVM also work in the same way of logistic regression. So if you see the linear SVM, that linear SVM concept is same as that of your linear regression. Of course, the non-linear SVM will use some kind of kernel trick and other things to do the task. So SVM the advantage of SVM is that for nonlinear data also it can actually do the classification task well by doing some kind of kernel tricks. So that is one cool thing about the SVM. As for neural network basis actually from logistic regression. So we have discussed logistic regression. No, that logistic regression is actually neuron. The logistic regression, ditto mathematics. You no need to change anything. That logistic regression is actually neuron. So multiple neurons, if you just include, then it's become a network. Multiple neurons means how each and every neuron is connected with other neurons. It's become a network. So artificial neural network, it's nothing but your simple logistic regression model only. Each and every neuron is actually logistic regression, but multiple neurons people will use to make the classification decision so that it's become neural network.
Okay.
So these are the other machine learning algorithms. I think some of those you will be studying in your coming courses. Other things you can easily go through it with the kind of things that we have discussed in this residency. Anything else? Any other doubt?
Okay, sir. The PDF I'll upload, sir. Both the PDF.
Yeah, sure, Lena. I will
Sure.
share those PDF to you. You can upload.
Sure. And sir, we are very thankful for all the sessions that you've taken, sir. Extremely grateful amidst the hectic schedule. Thank you so much, sir, for taking all our sessions.
Yeah, thank you, Lena.
Thanks a lot, sir.
Thank you, sir.
Yeah.
Thank you, sir.
Yeah, thank you all.
Thank you.
Daddy